9:30, huh?
9:30. Okay, so today I'm wrapping up, and today I know it's the last day. It's not quite last show, but we are towards, at least for me, it's my last show. I will be leaving immediately after my talk, or after this lecture. So if anybody needs, at any point, if you wake up in the middle of the night, dreaming of chimeras or worrying about Kuramoto, and, if you're pursued in your nightmares by Ott or Antonsen or anybody like that, please write to me, okay? My email is my name at Gmail, as it is for most people, I presume. Huh? What, you didn't get your name at gmail.com? I mean, look, I got it, and I've got one of the most common names in the universe, right? Anyway, it's r.ramaswamy@gmail.com, or without Google, whatever. But please, what I'm saying is that in case you have doubts of academic nature, please write. All other doubts, resolve them over beer, or don't resolve them, I don't care. Okay. All right, now, so what I want to do in today's lecture is to try to make some application of the ideas that we've developed in the last 3 or 4. And I'd like to tell you about some interesting phenomena that happen, which are purely collective phenomena, okay? They do not occur in individual systems. By definition, almost they can't, right? So the important thing about the collective phenomena is that in many cases, there are instances of phase transition-like behavior. I hesitate to call them true phase transition behaviors, but there are power laws and so on and so forth over there, right? So the two phenomena that I will talk about, one are the occurrence and the existence of chimeras. Okay, so the first doubt is whether it is pronounced chimera, it's pronounced chimera, or it depends on whether you're Greek or not, all right? For the most part, we will just call them chimeras, all right? So that's what this is. And it refers to the fact that in a ensemble of otherwise seemingly identical systems, you find the coexistence and the stable coexistence of different kinds, intrinsically different kinds of behavior, right? This is, to some extent like the coexistence of different phases, but not necessarily as simple as just, the presence of ice and water or something like that. But this is something that this is a dynamical phenomenon that arises as a consequence of the way in which things are coupled. Right? These chimeras were, they were discovered, these are mathematical chimeras, as opposed to the physical ones that you see a picture of, right? These mathematical chimeras were discovered many times, or at least twice they were discovered. Once in the study of couple map lattices, which I'm not going to go into the history of, but the most common reference is to the early work by Kuramoto and one of his postdocs, which was to look at this complex Ginzburg-Landau equation. Again, see, there are origins of all that in the kind of oscillators that Kuramoto eventually looked at. But basically, the point is that the coupling between these oscillators was neither purely local nor purely global. We've already studied the global coupling of phase oscillators in some detail. Right? We've seen that you have synchronization, no synchronization, phase transition, and so on and so forth. Okay. With local coupling, the problem is actually much easier to solve. And in fact, what you have are, these problems are in a sense integrable, easily solvable. Kuromoto on a ring has n constants of the motion, so it's a simple problem to solve. Okay. The non-local coupling is where you have the coupling between elements in a sense depends on a distance-like parameter, right? So the kind of equation that you look at is something like this, where this kernel is, the kernel has a dependence on x minus x prime, right? As opposed to we've usually looked at Kuromoto where the kernel itself was unity. It was independent of distance. All right. So, and sorry, this notation is a little mixed up because some slides are taken from some talks in some years when theta was phi and phi was theta. You will all reach this stage one day. That is the universal fixed point of any person who gives a talk, is that you recycle slides. Okay. So the basic phenomenology of a chimera is the following, all right? You've got a bunch of oscillators which are coupled identically to each other. By identical, I just mean that the formal expression is the same. So every, for example, if you've got oscillators on a ring and you're coupled to the, to the first neighbor, the second neighbor, the third neighbor with decreasing strength of coupling, each one of those oscillators has exactly the same behavior, right? And this is a slightly subtle problem, depending on the initial conditions and depending on how you do your simulations, after a while you find typically a snapshot like this. So the phases, what's called theta over here and phi over here, these phases are, for one group of oscillators, it looks like the phases are highly correlated, all right? So the phases just move smoothly from whatever, some value. It's almost like a continuous variation as you move along the chain. If they were completely synchronized, all the phases would be identical, right? So it would have been a straight line at some point in time. Instead of that, you find this kind of behavior. The oscillators on these two, this has got periodic boundary conditions, so, right? And there's a large part which are completely uncorrelated. So if you were to look at local order parameters, you remember the complex order parameter that we had in Kuromoto, R e to the I phi. So locally over here, R will be close to 1 because all the oscillators are more or less coherent. If I was able to do that, and I'm going to do an example, I'm going to do an exactly solved model where we'll see how R changes across populations. And over here, R is 0. Or if not 0, at least it's some finite value which is not 1, not close to 1. All right? So this is, in a sense, a complex asymptotic state. All right? Oh, it was touching. All right, and the non-locality is brought about by kernels of this kind. All right, so here is an example, a typical example that one could deal with. Kuromoto and Strogatz and Abrams and others, they dealt with cosines. For some obscure reason, I thought that having piecewise linear, these kinds of hats, this is a witch's hat or tent or something like that, that would be more interesting or more analytically solvable. But it turned out that it didn't quite have, the same behavior. But let me just show you that if you keep, it doesn't almost have, it doesn't have necessarily to decrease with distance. All you want is that it has a distance dependence. So here is an example where it decreases with distance, this decreases and is flat. Here it is flat for a while and then it increases as you get further out. And you can see all these various shapes that have been explored. It wasn't just a case of looking at, what can we explore all these various paths. At some point in time, we found that if you had, something which was uniformly decreasing, right, you managed to get a chimera with one region or one cluster which was completely disordered and another which was completely ordered. But if you changed the geometry around, okay, just had some significant region which was flat, then you could magically get a chimera with two coherent regions and two incoherent regions. And you change that, you got again two coherent and two incoherent. The difference between these two and these two is the question of the phases that the oscillators had. Then you could go around to you see that basically you can design the kind of chimera that you want by changing the form of the non-local coupling. So in a sense, this sort of gave us a lot of tunability as to what you could do with a chimera, and it also helps elucidate why you get chimeras and so on. Okay. All right. Yeah. So this complex behavior is typified by these kinds of movies where. Okay, so here you have one incoherent region that is largely this one, and one coherent region. So these oscillators are all spread out over the place. These are all moving together. Right? There is these have been designed to look like, in the sense, what is designed over here is that these are taken in a rotating frame. So in the rotating frame, one whole bunch of oscillators is fixed, and the others are moving at some other, in that frame. Here you've got two clusters of almost coherent oscillations and two clusters of incoherent ones. Here you've got another example, and so on and so forth. So, okay, so one can play around, and this is the meaning of this coexistence. And when you look at the coupling for any individual oscillator, it doesn't look different from anything else. So this is indeed a surprise. Okay. Space-time plots look, look like this, in the sense that as a function of time, what I'm doing is I'm plotting the phase, theta, as a function of time. These are other variables. I mean, let's not worry about these so much. You can see that the phases are oscillating between plus pi and minus pi in this group. And for these other groups, the phases are all constant. So these space-time plots tell you one thing about this kind of a chimera, that the oscillators that are part of the disordered set and the oscillators that are part of the ordered set, these change identities from time to time, particularly on the boundaries. So it's not as if once you are in the ordered phase, forever you're going to be stuck in the ordered phase. You could, the person who gave the name chimera and so on was Stephen Strogatz, and if you've read any of his papers or listened to his podcast, which I should recommend strongly, it's a very nice podcast. I think it's called The Joy of Why. Right, but that used to be a joy of X, now it is the joy of Y. All right, but he has all, he's sort of always bringing up these new terms and so on and so forth. So these are breathing, chimeras are not dead, they breathe. Okay, so they are breathing chimeras and so on and so forth. Okay, all right. In the same way, you could look at, in other geometries which we have studied, see, this is in a sense, it's a game that one can play to look at what kind of complex behavior can emerge if you have different kinds of geometries. And one particularly interesting geometry to look at are communities. So I don't know whether Sitabra discussed this kind of networks. He probably would have. So you consider a hierarchical kind of a network where you've got close connections between elements of one group and loose connections between elements of different groups. So the case that I will solve momentarily is where you have only two communities. Two groups of oscillators where the intra-group bonds are somehow stronger and the inter-group bonds are weaker. And one can do a fair amount of analysis. You find chimeras of various kinds, which, in a sense, I'm not even sure that they're interesting. Okay. One important fact about chimeras is that there is at the heart of a chimera is a feature called multistability, right? And multistability very roughly corresponds to exactly corresponds to the following situation: that at the same value, at a given value of a parameter, you can have more than one stable asymptotic state. All right? So think of a double well problem. You start out at some initial condition somewhere. You go to one of the minima. You start out another initial condition. You can go to the other minima. And both these minima, as solutions, they coexist. Right? So multistability is just a little beyond that in the sense that you have these attracting sets. These attracting sets can have different geometries. They can be strange attractors, they can be fixed points, they can be limit cycles, they could be any old thing. And the attraction can drive you from one spot to any of the attractors. Typically, when you have, let's say, if you've got this double well problem, you have like a boundary. You're on this side, you fall into this well. On this side, you fall into the other well. In multistability, you have something actually more interesting. All the initial conditions that go to a particular attractor are called the basin of that attractor. Right? Obvious, terminology. Everything that goes to, let us say, we take the Lorentz system, okay, just a simple Lorentz system. Everything that goes to the Lorentz attractor, I will call the basin of the Lorentz attractor, the attractor basin, right? If I start at the unstable fixed point, that unstable fixed point will not go to the attractor, but the basin of that attractor is just a point, right? So in the Lorentz system, what happens to the phase space is that you've got almost everything goes to the attractor. Then you've got 3 points that don't go anywhere. So you've got 4 attractors. You don't have 4 attractors. You have 4 asymptotic states. And these 4 asymptotic states have got 4 basins. If you have slightly more complicated attractors, it turns out that the basins of these attractors are very complex. In particular, the basin boundaries turn out to be fractals. All right? So now imagine that you've got 2 attractors and their basins are interlocked like so. If you start at one initial condition, you'll go to one attractor. If you start at a very close by initial condition, you can go to the other attractor. So you have extreme dependence on initial conditions in terms of which final state you go to. So this is a property called final state sensitivity. It's not just that the dynamics is sensitive with respect to the initial state, it is also sensitive to the final state. So the geometry of these attractor basins can actually be a very complex and important thing that one has to worry about. Okay. An example which may be familiar to you, because almost all of us have certainly done an experiment like this, is to toss a coin. Right? You've got a coin, and if I had the coin virtually, what I'd do is I'd toss it, it sort of spins around, and then it falls down, or I catch it in my hand, and there are two states. It's either heads or tails. All the initial conditions in terms of my initial velocity, the amount of angular momentum I give, etc., etc. What? You have a coin and you're planning to throw it? Right? No, or you owed him money. Right? No, the thing about thinking about attractors and their basins of attraction is reduced to some problem like this. Clearly, whether it's going to fall heads or tails is going to depend on a number of factors: how high you toss it, how much velocity you give, how much angular momentum you give, what is the mass of your coin, and so on and so forth. How large is it, what is the air resistance, and so on. But we know that finally there are only two states that are possible. Three states. You fall heads, you fall tails, and if you're evil, you fall absolutely on the edge. But most of the time, you're not evil enough for that, right? Okay. So now the question is, why do we trust, that India versus Pakistan match is going on? The referee calls everybody, the umpire, he calls them and says that, say heads or tails, and then he tosses it, and you trust it. Why? Because you think that the outcome is really a matter of chance, 50-50. Okay? But it's going to be a matter of chance only if, for every initial condition with which you throw the coin, there is a nearby initial condition that will lead to the opposite side. Right? Because whether I toss it like this, or I toss it like this, or like that, I'm always going to get heads, you're not going to believe that, right? So there is one very fundamental property about the basin of attraction of heads and the basin of attraction of tails, that they are strongly meshed together. It turns out that it's not nearly as pretty a story as I'm telling you right now, but I'm just saying that our assumption of the independence of these two outcomes is dependent on a certain idea we have, not about the coin, etc., but about the nature, the geometry of the basin of attraction. All the initial conditions that will lead to head are very close to other initial conditions that will lead to tails. And it doesn't matter how close you go. So if you take a volume of initial conditions, there are as many, the volume of initial conditions, sub-volume that will go to heads versus that which will go to tails is equal to a half. No matter how small you make that volume, and no matter what geometry you take that volume with. Okay, that is our idea. So that underlies our idea of fairness of the coin. Okay. Now this property of two basins of attraction coming close to one another is actually quite common. And this is a feature which is called intermingling. So just the technical term for it. So what happens in some systems, all right, is the following. So here what I've written down is sort of a dynamical system over here corresponding to n coupled Lorentz attractors. Okay. In the absence of this term, put k equals 0, this is just the Lorentz system. Okay, let me remind you again about the Lorentz system. It was linear in this equation. It had one nonlinearity in the y equation and one nonlinearity in the z equation. And what I'm doing is very simply to just couple them through the z variable. Okay, all of them are just diffusively coupled, the linear coupling term, through the z variable. Now, in the absence of coupling, there's only one attractor. For each of these systems, there's only one attractor, and that is the usual butterfly attractor. This is the one that, at least many of you would have seen before, and if not, I talked about it the other day. Right. Once you couple them through this, some interesting stuff happens. Particularly, if I take this value of the parameters, if there is no coupling, all right, for no coupling but at this value of the parameter, there turn out to be actually three attractors. There is a fixed point over here, there's a fixed point over here, there are two of them in the middle of these eyes, and you've got this strange attractor over here. And the basins of these three attractors, the basins of these three attractors look like so. That is, okay, I'm sorry, the resolution is a little bad, but all this light blue corresponds to initial conditions that will go to the butterfly. All the blue go to one of the fixed points which lies on one side. All the red go to all the fixed points that lie on the other side. The moment you add in coupling, this is what this is what the basins look like. So I've got all the, this is a term which has been called riddling. The basin of the big strange attractor has got points which correspond to going to the, to a periodic attractor, right, to the fixed point. And even in these basins, you have points that will eventually go to the strange attractor. This is not as complicated as it can be, but you can see that by just coupling them slightly, which is small coupling over here, the basins of these various different attractors have got really closely engaged with each other. So an initial condition that starts over here, even if I take a group of initial conditions over here, I'm going to have three finally different kinds of asymptotic states. Yeah?
You're assuming that all the oscillators have the same initial coordinates? You're only plotting one XY, but you have multiple oscillators.
Yeah. Well, this is representative. This is just for the case of two. Okay. This is just to show you what happens when you couple two of them.
But the two are being released at the same position?
Yeah. And you see, this is your initial condition in X and Y, and there's some particular value of Z. This is of course it's generated from a calculation, but this is just to tell you that how these basins are completely mixed with each other. All right? Yeah. There are details. So now imagine that you have a set of coupled Lorentz oscillators, and you just choose some group, some set of initial conditions, right? The moment you have coupling, where taken k is equal to some number, it doesn't matter, the basins of attraction are really, they go like so. So no matter what you do, you can never have a pure state. So you will automatically have some that will go to the strange attractor, some that will go to one fixed point, or some which will go to the other fixed point, right? And you automatically have a chimera. Because if you just take an ensemble of such systems, arbitrary initial conditions, some of them land up in one state, some of them will land up in the other state, and so on. But these are frozen. These don't breathe. These frozen chimeras are such, they are a consequence of the initial conditions that come about. And you have, one set which is in one fixed point, here's another which is in another fixed point, and here are the ones that are on the strange attractors, and the relative populations never change. Okay? So, in a sense, the chimera, and if you switch off the coupling, all of them will just immediately relax to the single chaotic attractor. So in the absence of coupling, there is nothing else. Everything just goes back to wherever it was. Okay. So this is a form of dynamical symmetry breaking that occurs spontaneously, and it's dependent on the coupling. If you had no coupling, you would not have a chimera. Okay. So it turns out that there's one interesting model that can be solved exactly, and let me just take you through some of the derivation of that. It was a model that came from Strogatz and his group, and it is the following. You've got two communities of oscillators. One group, there's some n of them, which are coupled strongly to each other. So you've got these two communities where the coupling inside the group is strong and the coupling between the groups is weak. All right? I'll write it down and we'll discuss it. Can I just have the board now? Yeah? Three. The number of bases, okay, there is actually an experiment by a Polish group where they take 3 pendulums and show that you have a chimera in that. Okay, I haven't studied it in too great a detail, but what the number of, can you just switch this off? Yeah. Okay, I'd just like you to keep this picture in mind, namely that you've got one group which is fixed, and these are all in synchrony, and the other group which is, async. All right? Okay, and the reason I thought I would do this is also because, it's an application of the Ott-Antonsen model. So we have, in a sense, a mean field theory that we can apply to it. All right? So you've got this community over here. Let me call that. These are two communities, sigma is equal to 1 and sigma is equal to 2. All right? And you've got these oscillators over here, so these are all coupled one to the other. And you've got all of these coupled one to the other, and then you've got these coupled in between. All right? So the equations for the phase are the following. So d, in what follows, theta and phi are to be considered to be the same. So I'm taking the ith phase oscillator in community sigma. Sigma goes to 1 or 2. This is just equal to omega. I'm not going to bother too much about omega. Plus, and here is the sum, over the communities 1 to 2, k sigma sigma prime divided by n sigma prime. The number of oscillators in each community need not be the same. Okay, so, all right, and I'll say that K11 is equal to K22. So this is the couplings inside a community, and that is equal to mu, which is greater than nu, which is the coupling between community 2 and 1 or 1 and 2. Yeah? So it's clear? So the coupling inside this community is K11, K12, K22, and the coupling of this to this is K21, and the other way around is K12. All right? Okay, so I'll have some new variables. All right. So this is a phase shift parameter over here, right? And lots of things depend on these phase shift parameters, so it's not you can't set it equal to 0. In fact, interesting behavior usually happens when beta, which is pi by 2 minus alpha, that is close to 0. Anyway, some of these details are not that crucial. It's also, for whatever reason, it's normalized so that nu plus mu is equal to 1. And, okay. So we think of this, of course, as a phase velocity. So let me call this Vi of community sigma, right? And that is just equal to this quantity, right? Okay. Now, okay, so recall what we need to do for Ott-Antonsen type of analysis. We're going to the large n limit, and we'll think in terms of some density, rho, but now there are going to be two densities that we have to worry about. Rho, because rho is going to now depend on sigma or sigma prime, right, depending on 1 and 2, and it's going to depend on the angles theta. And I'm keeping all the omegas identical. I'm not bothered about the distribution in omegas. Okay, let them. So I just have theta and t. So this is my density. Okay. If this is my density, then I can write an order parameter z sigma of t. This is just equal to the summation over sigma prime is equal to 1 and 2 k sigma sigma prime integral e to the I theta sigma prime rho sigma prime theta prime t d theta prime. Actually, let's forget about putting sigma because all of them are sigma prime or not primed. So just keep that as a, okay, so just that notation, right? So rho prime means rho sigma prime, theta prime means theta sigma prime. And sigma is just the index of the community that we are integrating over, all right? So now I've got that V sigma. This is just omega plus 1 over 2I. We express this as a e to the I whatever. So let me just say that this is equal to z sigma e to the I alpha e to the minus I theta minus z sigma star e to the I alpha e to the I theta. So that using this notation for this quantity is your order parameter, right? This is what we were calling R e to the I psi in the Kuramoto case. This is just Z, and it's just the integral of e to the I phi over this particular thing, right? E to the I theta in this particular case. So we've got this equation. Which I can, right? And so basically what I've done is to take this definition, take the sign, express it as an exponential over here, regroup the terms, and we get an equation like this. Okay. And all right, so this is my expression for the velocity. And obviously, this is just equal to d theta by d t, d theta. Yeah. So in Ott-Antonsen terminology, what I need to do now is to look at rho and do its Fourier decomposition. So if I do that, I find that rho sigma of theta and t. This is just 1 by 2 pi summation of n going from minus infinity to infinity, a sigma n. Okay, this is a sigma nth Fourier component e to the I n theta. But Ott Antonsen said that the nth component over here is just equal to a to the power n. That is the ansatz. We replace all the coefficients a sub n by a to the power n. Okay. This is an approximation, but a very good one. We've gone through this in the last 2 classes. All right? So now taking this form, putting it into the following equation. So the equation that we have to worry about is d rho by dt is equal to okay, so d rho by dt is equal to minus d by d theta of v rho. The zero noise Fokker-Planck equation. Putting that in, you finally come down to, let me just rub that out over there. Putting that in, you finally come down to the following equation, that is d rho d rho sigma by, well, let me not go through all the painful algebra. I've got rho over here. I take the time derivative. I can take the derivative with respect to theta, all right? Bring out similar terms, and finally I get the following rather nice ordinary differential equation: a sigma dot plus I omega a sigma plus 1/2 a sigma squared z sigma e to the minus I alpha minus z sigma star e to the I alpha is equal to 0. Okay, some of this you can sort of verify and check, all that doesn't seriously matter. Basic point is the following. I've got these 2 communities, I've got these 2 densities, and in both the cases I make the approximation that the Fourier transform, the Fourier decomposition of the density, the coefficients over here are just some constant raised to the nth power. And all these numbers are less than 1. Okay. So when you do that, the infinite number of equations just settles down to this particular equation, which you can then solve. Right? And this equation has a straightforward solution. Once you solve for the a's, from there you can get your order parameter. That z sigma as a function of time, this is just equal to summation of sigma prime is equal to 1 and 2, k sigma prime, that's that thing over there. Now, I can do this integral because it's only one single theta over here. It is just a sigma star as a function of time. Oh, sorry, this doesn't have time in it. A sigma prime star. Okay, so this allows you to get the order parameter in a very straightforward way from the using the Ott-Antonsen ansatz. Now what Strogatz and company did was to go a little further and try to obtain an equation for how how does the order parameter change as a function of time, right? Now, for that to be, for that to be done, you basically, you see, the order parameter over here is just equal to the first component, A1 and A2. That's all it really depends on, because these are the two communities over here, right? So what they went on to show is that you can solve this in the following way. Okay, so 0 is equal to A1 dot plus I omega A1 plus 1/2 of A1 squared Z1 e to the I alpha minus Z1. I'll just discuss this in a moment, e to the I alpha. Okay. So I'm basically writing down the stationary condition over here, because I want to know what is the stable behavior in the two communities. So here is one equation, which I can obviously get the second equation straight out of this, this is equal to the same thing as A1 plus I omega A1 plus 1/2 A1 squared. I want to get rid of the z's, okay? So A1 squared to K11 A1 star plus K12 A2 star times e to the minus I sigma, I alpha minus 1/2 K12 A2 plus K11 A1 e to the I alpha. Okay, the thing is that I've gone through the derivation over here. Some of it is not worth repeating. But the basic point is that I want to now get a condition which will allow me to write down the order parameters for the two communities. And what I would like to show, if I'm going to have a chimera, the order parameter in one community should be 1, and the order parameter for the other community should be less than 1. May not be 0. It would be nice if it was 0, but it may not be 0. I'd like to show that these two communities have a state where both the order parameters can be distinct from each other, with one of them 1, one of them non-1. Okay? So the procedure is really as follows. You write down your model, you write down your densities, you make the Ott-Antonsen ansatz over here, feed this back into the original equations, and once you fed it back into the original equations, you get these equations for the Ott-Antonsen amplitude. The A1 is just the amplitude of the Ott-Antonsen solution in a given community. Having done that, and you wouldn't do it unless it gave you the right answer, you find that R1 dot is equal to minus R1 squared minus 1 by 2 into mu R1 cosine alpha minus nu R2 cosine of phi 2 minus phi 1 minus alpha. And phi and theta are the same, is equal to omega minus r squared plus 1 2 r1 and some additional terms over here. Let me not go on to that. Basic point is that once you've gone through this entire lot, you come up with a solution for R1 dot, which has got leading terms like this, right? And you can see immediately that R1 is equal to 1 is a stationary solution for this equation, okay? So after all this work, basically what you're able to show is that community 1 has a stable solution where R is equal to unity, namely the fully synchronized state. Okay. Similarly, doing the exercise, going to the next community, you find that R2 dot, that is equal to 1 minus R2 squared by 2 into mu R2 cosine alpha plus nu cosine of some other angle, all right? And this also has a solution where R2 is equal to 1. That will also be a solution, but it's not difficult to show that you have an additional solution where R2 is not necessarily equal to 1. Namely, from this particular equation, you can get some solution where this term is not 0, but this particular term is 0. There's the way in which these two systems work out is like that. And some of it is really the algebra that you have to do in order to see that it all works out. But what I wanted to convey to you, really, and I'm not entirely sure it's been successful, is the following. That if you take different communities and you extend the Ortantons ansatz to these various communities, you can show that these are consistent with having different solutions for the different communities, and therefore you establish that you could have these chimeric states, right? The feature of the spontaneous symmetry breaking is not easy to see over here, but let me just say that experimentally you find it, and so one sort of trusts it that this happens spontaneously. Okay. Now, since the time these papers were written, which was in the early part of this century, so these all go back to about 2002, 4, 6, something like that. There's actually been a huge amount of work on different kinds of chimeric states, not just in 1D, but also in 2D, 3D, etc., etc. So there's a lot of interest in this kind of symmetry breaking. Large part of it is due to initial conditions. There's a lot of dependence on initial conditions and so on. And let's just say this is a field where there is a lot of interest. Different kinds of oscillators, different kinds of coupling, what kind of chimeric states do you get, etc. All right. So let me stop over here with discussing chimeras, because there's another phenomenon that happens in these coupled oscillator systems that I'd like to talk about. Okay. All right. See, in addition to the simple phase oscillator model that Kuramoto dealt with, there's some other standard harmonic oscillator type of systems that people in this business and dynamical systems have looked at. One of them has to do with the following situation. Right. Let me write it in polar coordinates. And I'll actually let me not write it in polar coordinates. Okay. Okay. So this is Z is a complex variable, right? And alpha is also complex. Let's say it has a real part. Alpha plus I beta, okay, and this is an approximation to the Ginzburg-Landau equation. In fact, it's called the Stewart-Landau equation, and where Z is a complex variable. So sometimes people write it as x plus I y, and then you can write it in 2 dimensions. Okay, Now this system has a very simple, I mean it's nice behavior. It has a limit cycle. You can see that this, z squared is equal to alpha plus z squared is equal to alpha is fixed, right? So, and there is another fixed point which is 0. When z is equal to 0, the origin is a fixed point, okay? And when z is equal to, when the radius of the circle is equal to alpha, for example, you find that that is also fixed, right? So this is a limit cycle. And here's your stationary fixed point. Okay. It's not difficult to see that if alpha is positive, this limit cycle is your only stable behavior. And if alpha is negative, your fixed point is your only stable behavior. Just take the derivative, the slope at the origin will be okay, so I'm just assuming the linear stability analysis will tell you these two following cases. So for positive alpha, I have a cycle, and for negative alpha, I have a fixed point. What this means is that if I was looking in variables x and y, if I have positive alpha, I will eventually get oscillations. If I have negative alpha, I'm going to get damped oscillations, right? So this is a system. Now the question that was asked by Daido and Nakanishi and a whole lot of people after that is the following. Consider that you have a population of oscillators, right? But this population doesn't have all the same parameters. You have a spread in the kind of parameters that you have. In particular, supposing you have a distribution in the alphas, some of them being positive and some of them being negative, right? So if you have, you see, you've got a large number of the same kind of system, but you have a dispersion, a spread in the parameter values. We looked at systems where you had a dispersion in the frequencies and so on and so forth. So this is just another kind of dispersion to look at. But here, there is a consequence. What are the consequences? If you start with a group of oscillators, which are, some of which have got negative alpha, all of those are going to damp down and stop oscillating. All the ones that have got positive alpha are all going to be oscillatory forever. Right? Okay. Now what happens if you couple these two? All right? So the game that these people played was to take n oscillators, okay? And of these n oscillators, p, this fraction p of them had alpha negative, and q of them, that is 1 minus p, had alpha positive. So you've got this population where there is, just by the diversity of parameter values, there's some fraction which are going to die out. So these are called inactive. As a function of time, what would happen is that they'd all just become inactive, because damped oscillations. And this fraction would have positive alpha, so they were called active. Right? Okay, so the question that was asked, and it's just something to think about, is that what happens if I have some group of active oscillators? The definition active only means that asymptotically, in the absence of coupling, they will remain oscillatory. And another population which, in the absence of coupling, will all damp out. What happens if I couple the two of them? right? So just thinking from one point of view, I mean, you've asked these questions in so many other contexts. You've got some magnetic systems, you've got some non-magnetic systems, couple them, what happens, right? So it's not an unnatural kind of question to ask, but one can also already think about what might happen. See, what we've seen when you study dynamical systems and you couple them, is that when you take two systems, we've coupled them using, in the idea of synchronization. One starts behaving like the other. You've got an oscillator, you force it with something else, it starts having characteristics of the other and so on. So one could expect that if I take an active system and an inactive system, depending on who the boss is, either the active system will die out or the inactive system comes up. Right? Okay. And it turns out that that's actually what happens, but it depends on this parameter P. How many of the oscillators to start with are active, how many of them are inactive, and what is the strength of the coupling between the two. That sort of tells you what the dynamics is going, what the asymptotic dynamics is going to be. All right? So let's just ask him to. Is this the one? Okay. Is it done? Yeah.
Can the spontaneous event breaking be thought of as some minima of a Ginsburg lambda free energy? I mean, I'm not sure if this is the correct analysis, but
I've never seen it described in that particular way, but it's always, see, the only analysis that is, okay, there's phenomenological analysis, and I don't want to get into that, right? But all the other kind of, analytic theories for a chimera, and I've given you a reference to Omelchenko, so you have a look at it. I don't see it as a minimization problem. See, what is a more common way of thinking about it is that it's a bifurcation out of some state, right? But that it is a minimum of something I have yet to see, right? All right. Achha, before I come to the idea of what happens in communities, let me tell you about a phenomenon that occurs in a simple example of two coupled oscillators. All right. What I have over here is, right, so here is an example. Just let me remove this over here. So this is your ordinary Stewart-Landau system, right? I had just written it down with general alpha and beta over here, but I just think of this as one Stewart-Landau equation where alpha is equal to 1. So the asymptotic dynamics of this one Stewart-Landau is to go to a limit cycle which will have radius 1. Okay, so the dynamics in the Z plane is going to be X and Y are going to oscillate in time. All right. Now, if I take two such such oscillators, you see, the Stewart-Landau is a very popular system to use because it shows it's sort of the standard behavior of any oscillator near what's called a Hopf bifurcation. The Hopf bifurcation is a very general bifurcation that happens in dynamical systems. It's an important one because it sort of answers the basic question, how does a system start oscillating? Right? See, when you have a system that is, see, in a typical system, you have, let's say, you have a stationary state that is stationary, is just a fixed point, right? If that fixed point becomes unstable, then the system starts oscillating through a very sort of straightforward mechanism of just going around a circle. It bifurcates out of that fixed point and it goes into an oscillation, right? The way in which this happens is by looking at the eigenvalues of the Jacobian at that point. The eigenvalues for a fixed point are all going to be negative. If you've got your basic oscillation, the eigenvalues have to go through the imaginary axis, right? You've got some eigenvalue which is e to the I something, right? So this is your basic Hopf bifurcation. So the Stewart-Landau is very important for studying that. You know, as this parameter goes from 0 onwards, you have the Hopf bifurcation. What is quite surprising is that if you take two oscillators of the same frequency and couple them in a straightforward manner like this is diffusive, as you change the value of the coupling, you have something called amplitude death. By amplitude death, all it means is that the oscillations at a certain point just stop and the system damps to the fixed point. This is a much more important phenomenon than you think, or than you might think, right? Because whenever you want to damp an oscillation, how do you damp oscillations? I mean, usually you think you put a lot of weight or some such thing like that. That's really not how things get damped. Anyone who's driven in a car, your suspension is an oscillator, right? In order to have your suspensions not oscillate you away to, see, the reason why a car remains stable even though you go over bumps is not because the car is infinitely heavy, which would be your usual way of thinking about damping an oscillation, right? Just increase gamma. No, that's not how it happens. How it happens is like this. You do quench your oscillations by forcing it with something else. You see, this one is oscillating. This one is also oscillating, but the way in which you have combined them can drive you straight into oscillation quenching.
So both the oscillations die?
Yeah, both the oscillations are diode. Because this is symmetric, you can make, there are enough people who have worried about all these kinds of problems. So you have one of them quenched, one of them not quenched. You have chimeras where some of them are dead, some of them are not dead. All sorts of stuff happens. But I'm saying, the basic phenomenon that I want you all to appreciate is that if I take two oscillators, couple them in a certain way, you can make both of them stop oscillating. Right? Now, in this region, which is called amplitude death, what is stabilized, okay, this is some analysis we did some years ago, but what is stabilized is the original fixed. See, every oscillation arises out of some fixed point. There's a fixed point, it became unstable, so you're oscillating around that fixed point. If you stabilize that particular fixed point again, that's when you have oscillation death. You could add other terms to your system, and instead of stabilizing your original fixed point, you stabilize some other fixed point. Again, you don't have oscillations around this fixed point, but the phenomenon is called oscillation death in one case, amplitude death in the other case. Historical. All right? So the point is the following, just what I've said. In the absence of coupling, the dynamics is oscillatory, the fixed points are unstable. Due to the coupling, the equilibria are they've sort of made stable again, and the dynamics is no longer oscillatory. This is amplitude death. There can be new fixed points that are created, and it's called oscillation death. And the basic point over here is that in both cases, you just don't have systems oscillating anymore. All right? Okay. So this is just the behavior of two oscillators. Now I am asking you to think in terms of populations. I've got n oscillators. P of them are essentially inactive. 1 minus P of them are essentially active, and now I'm going to couple the two together, right? What Dido and Nakanishi found, all right, and they called this phenomenon aging. What they found is that if you increase the proportion of inactive oscillators, that is, those oscillators that are eventually going to die out, but if you increase this population, right, then at a certain point, it takes over the dynamics of the entire system and everything comes to a grinding halt, right? And I don't like the term, but they call this aging, in the sense of everything stopping being active, right? Yes, I do take it personally. No, I mean, in the sense that I don't see any phenomenon like aging in this system. It's not, I prefer the name stasis, that's why I keep using the word stasis. Let me say that the international community hasn't exactly rushed and said, yes, yes, we'll call it stasis, Ram. Anyway, so the point that I want you all to, in a sense, think about, which is very natural when you're talking about ensembles of dynamical system. See, given a dynamical system, there's almost always a parameter which is of interest, which as you change the parameter, the behavior will be different. Okay, this just goes without saying, right? And there could be bifurcations, because with some parameter you change it. In the Stewart-Landau, for example, if alpha is negative, you have a fixed point. If alpha is positive, you have an oscillation. So instead of thinking of ensembles of identical systems, now think of heterogeneous ensembles. If I have a whole range of parameters, and this is very common, I mean, in nature it is more normal to think in terms of heterogeneity, even if not in the kind of dynamical systems, at least in heterogeneity in parameters should be a sort of a thing to worry about. Okay, so this was the initial motivation. So what they did was they took a set of these Stewart-Landaus. This also gets to be a little tiresome, but everybody looks at Stewart-Landau, all right? But okay, so you take a bunch of Stewart-Landau, and now you have got the imaginary part is not that important. So just take different alpha j's, right? Some of the alpha j's are taken to be positive, equal to A. Let's say all of them are equal to A. Some of them are taken to be negative. All of them are equal to minus B. All right? So that is the thing that they did. And you can sit around and do a mean field analysis. If A is your average active oscillator, it follows that equation. If I is your average inactive oscillator, it follows that equation. Okay, I've given you the reference to Dido Nakanishi, so you can look at that. Okay. The second thing that they did was to introduce an order parameter. This is actually a very trivial order parameter. And this parameter is the following. What is the average value of the x variable? Z is written as x plus iy. So what is the average oscillation? If everything is dead, then this quantity, this is going to be 0, let's say, and the average is going to be 0. So you basically will have this quantity m is going to be 0, if that's your average oscillation. And so this is just a way of finding out how much activity is left in the system, all right? So this measures, this is your average of the x value, this is your actual x value, so this is like a whatever square separation. I mean, it's sort of a fairly trivial kind of order parameter, if you like. Okay, normalize it to 1. So, see, remember that if the fraction of inactive oscillators is equal to 0, everything is active. All right? So you just normalize it to that activity. Okay? And what they found was something like this. They were able to calculate the critical transition as a function of the coupling, this order parameter goes smoothly from 1 to 0, and at a certain point over here, you actually have a transition. So here is k equals, I think it's k equals 8 over here. So if k is equal to 1, there is very weak coupling, then your activity in the system gradually decreases until the fraction of inactive oscillators goes to 1. See, p equals 1 is every oscillator is inactive, and p equals 0 is every oscillator is active. All right? The interesting part over here is that at a non-trivial value of p, the activity in the system goes down. So this is where you would have had, this is where the aging transition actually takes place, that even though you've got a system of coupled oscillators, because of diversity, beyond a fraction of about 0.75, everything is just taken over and made inactive. All right? And for this simple system, you can actually calculate this, it's critical probability. It's not any threshold as such. Any critical probability is there, and this is their, this is their basic result. At this as you go across this transition, things have power law dependencies and so on and so forth. I don't want to get into that because it's very particular to that system. All right? Okay. Interestingly, if you take dimers, that is, if you take, instead of having a system in 2 dimensions, you take a system in 4 dimensions consisting of this Stewart-Landau dimers, that is 2 of them coupled, right? So if these terms were not there, you would have had, if the epsilon terms were not there, you basically had a two independent Stewart-Landaus. And here, this is a way of coupling them so that you have a dimer. All right? The interesting thing here is that you go from 2 dimensions to 4 dimensions, and I'm not going to there's a fair amount of detail over here. Important thing is that, of course, 0, 0, 0, 0 is a fixed point of the system, but it also turns out that there are 2 other fixed points which are equally interesting. The only reason I brought this up is that to show you that in such systems, the phase plane, that is, here is a question of the population of inactive oscillators, and here is the coupling. The phase diagram is actually quite interesting. You have a whole lot of different behaviors, and I wanted to particularly show you what the effect of coupling active and inactive oscillators is. If you've got the active oscillators, they are oscillating with some frequency. The inactive oscillators are at fixed points. But because of the coupling, these fixed points are not rigidly fixed. They are oscillating, small oscillations about that. So what happens when you've got a heterogeneous ensemble is that the activity of one system induces a little activity in the other. At some point, you go to global synchronization, and as you increase the proportion of, you're going along this line over here, further down over here. As you increase the proportion of the inactive oscillators, you go immediately to complete oscillation depth. Okay? In this system, what is interesting is that you actually have a first-order phase transition. You have an abrupt transition from order parameter close to 1 to order parameter close to 0. So showing that the transition, the way in which the aging happens, I mean, it's not really aging, it is like heart attack or whatever, boom. In the business, these are called explosive transitions, and this is unimportant.
So
Yeah.
it was not clear how is this system different from the previous system. So instead, so you had just two oscillators. But was the coupling also different?
Well, see, in this particular case, okay, if I rewrite this in terms of x and y, right, this is just a two-dimensional system. Forget the coupling.
We have many oscillators, right?
Okay, so let me be clear now. A given Stewart-Landau oscillator, all epsilons equal to 0, is just in a single complex variable. So I can rewrite it in terms of real and imaginary, right? So this would be a two-dimensional system. This would be another two-dimensional system, and they are coupled, all right? What I've done over here is to have two Stewart-Landau. These are two uncoupled Stewart-Landaus written in terms of real, imaginary. But now I have just coupled them, these two. So this is now actually a four-equation system. This is a system in 4 dimensions.
No, so previously you also had epsilon times z1 minus z.
That was, yeah, but then once I switched off epsilon, I went to two uncoupled systems. Here, this is your basic unit. And I'm coupling together large numbers of these.
Oh.
See, it's a question of whether your n systems are two-dimensional systems or four-dimensional systems.
So there is an epsilon in one unit itself. There is another coupling parameter.
There's another coupling parameter for the others, right? Okay, so there are, I mean, the point of this was just to show you that it doesn't always have to be a second-order phase transition. In such systems, you can even have first-order phase transitions or discontinuous transitions, which in this business are called explosive transitions. Okay, so that actually brings me to the end of this set of lectures. What I have tried to show you, with varying degrees of success, I imagine, is that dynamical systems or large groups of dynamical systems, ensembles of dynamical systems, can actually serve as nice paradigm models for statistical behavior in terms of both emergence of interesting kinds of collective states. The 3 or 4 different collective behaviors that I've tried to talk about. First, of course, is complete asynchrony. It doesn't emerge, it is just there for you. It's complete disorder, called complete order, that is complete synchronization. And then within synchronization, you can have this interesting coexistence of synchrony and asynchrony, that is the chimeras. And depending on the level of heterogeneity, the other kind of collective state that could emerge is either collective activity or collective inactivity. Okay, so that's it. Thanks. It's unfair to ask people on the last day. That's why I started this lecture by saying, if you wake up in the middle of the night unable to sleep because of chimeras or death or whatever, or aging, please feel free to write to me about it. Yeah?
Is this what happens during this cardiac arrest?
Some versions of these do happen because when you have groups of cells that are completely in synchrony and one group goes out of synchrony, then it could happen that one behavior overtakes the other. So there are many phenomena that have interesting analogies. I have not tried to sort of, assert that that you have 1:1 correspondence between them. But people do think of, one of the common applications of chimera states is this situation where one half of the brain is allegedly switched off and the other half of the brain is allegedly active, right? And this group of oscillating states and group of asynchronous states is like half asleep, half awake. So, it could have, but I don't know whether it's of any value more than just an analogy. Yeah.
Okay, so let's thank Mr. Ramanujan for a wonderful
Now I'm leaving. Without the mic.
Okay, so I'll probably start the last lectures while everyone else is sitting. So again, a short recap just to, even for myself, I think it's useful. So in the second chapter, I try to describe this mean field construction to describe the glass transition with many interesting features that can be worked out and understood in great details. And at the end of the lecture, as I said, but when we go back to finite dimensions, there are many things that don't work and that we don't understand very well. Hence the need to do more statistical mechanics studies. So what I did mostly yesterday is to try and do the following. I didn't want to give you the impression that, it's when you do the mean field theory with small corrections, it's all understood, everyone agrees, and there is no fight, and it's like there is a consensus in the community. So what I try to do with the lattice model is to show you that there is a broad diversity of approaches, and I've tried to give you like an extremely different approach in terms of this lattice glass model with rare defects that kill everything, and we looked at these constraint models. In those models, there is no such thing as interesting static properties for the glasses. So everything in the chapter 2 goes in the trash, and then instead you think about dynamics in terms of this gas of defect with some kinetic rules that may lead to interesting physics. And at the end, I said if you construct another family of lattice models, the lattice glass models, they have everything in them, it seems, so they look a bit as complicated as the real system. They have interesting thermodynamics when you go to the mean field. The whole random first order transition construction seems to apply. You go to 3 dimensions, you do measurements, you see traces of this. You look at the dynamics, you also see defects and this dynamics facilitation thing. So telling you, depending on what you're studying, it's not easy to make strong conclusions. And moving from the mean field to the real world, it's not terribly easy. So that's the plan for today. I want to go a little bit closer to the real world than the lattice glass models. So the lecture for today would be a discussion of atomistic models for glass-forming liquids. So that's the last chapter. So atomistic glass formers. And from the questions and the discussions I had with many of you are already doing computer simulations of these particle models to study the glass transition, but I'll go slightly over their definition and stuff at the beginning, and then spot a few results to make the connections with everything we said before to try and close the loop in the last lecture between the intro and the theory and the models and the simulations. So I had, some discussions about this. Many of you are doing simulations, and probably you have answered that question already. So why do people do computer simulations of lattice models? Well, essentially, it's the outline of my lectures. I started with, you have experiment on the real complicated molecules, and then extremely far away, say in infinite dimensions, you have the mean field theory. And it's very nice, very beautiful, but it lives in this corner there. Then yesterday I say, well, we have interesting lattice models. Some of them agree with, the phenomenology of the experiment. Some of them show the features of the mean field theory, but it's complicated. So this is where I would put the atomistic models. So they live very close to the experiments in the sense that even though we don't simulate very complicated molecules with all the chemical details of the molecules, it's still particles that live in continuous space with interactions that are not too unrealistic. So in terms of what you put as an ingredient, as a starting point, it's very close to the experiments. It's easy to compare to the lattice model, and it's easy to certainly look for traces of the mean field theory, the random first order transition, these complicated static signatures. You can do everything in the computer simulation. So what I like is they are realistic, but simple. And simplicity is the key if you want to understand something and throw away, a lot of the complexity. Simulations really, you all know that. It's really easy to do. Anyone can do computer simulations after just a few days of learning. And what I think is really key for me is test and measure anything. Okay. And to me, that is the key. That is, because you have access to all the positions of all the particles at all times, you have all the information you like, so you can compute anything. And of course, the trick is to be able to extract useful and interesting information out of the anything, and that's the goal of learning how to do those things. But in principle, you have all the information you like. You can compute any of the weird quantities that we have discussed within mean field. In principle, it's there. If you work hard enough, you can extract that information. And that's precisely why I think the simulations are really useful. You can do computer simulations in dimensions 4, 5, 6, 7, 10, 12, 20 if you want, and try to see whether you see hints of the mean field limit that we have discussed. This you can do. So really you can measure anything, at least in principle. Doesn't mean it's simple to do, but conceptually it's doable. And that's the reason why I think computer simulations in that field are useful. By contrast, experiments, of course, are the reality we want to describe, but measuring everything and anything in experiments on molecular systems, with atoms or small molecules, it's terribly complicated. Hence the need for the same spatial resolutions, but with, detailed information. So what are the canonical models that we use? So what are the types of models? So I said we will take particles in, say, 3 dimensions. They will live on continuous space, and then the simplest way of describing a liquid, the simplest way, but it's not, people have invented more complicated way is to take classical models, so you forget about, the details of, the chemical reactions and the electrons and everything. So you go to classical models. You take pair interactions, just again because you want simplicity. So, you forget about many body forces, for instance, just to be simpler and simpler and simpler. And you forget about the shape of the molecules or the size of the molecules, and you study points. Okay? And that's already considerable simplifications compared to this, but you keep the idea that you have particles in continuous space. Okay? That means you study Hamiltonians like this. And it's already good enough to understand a lot about the statistical physics of liquids in glasses. Okay? So the potential that everyone has already discussed a lot in that room. So the potential that people have introduced and used a lot in the development of liquid state theory is the Lennard-Jones potential. So just write it down for the sake of it. Okay, so this is the Lennard-Jones potential. And you've already seen that guy. So let's think a little bit about what is the physics that Lennard-Jones has put in it. So R is the interparticle distance. Sigma and epsilon are two parameters for now. So quite obviously, epsilon, we know what it is. It has the units of an energy because the potential has an energy. So what is sigma? Sorry? The diameter of what? No. We are studying points. There is no particle. There is no diameter. Remember, sigma is just a parameter, right? It means nothing. It's just the unit of length. It's giving you the length unit. It's not a diameter because particles are points. So physically, of course, you're right. It has the feeling of a diameter. I'm just making the point that you should remember you don't have particles. There is no internal degrees of freedom. These are points. And sigma and epsilon together are telling you how close two particles at a given energy can approach each other. But apart from this, sigma is just the unit of length. It's a number. It's a parameter. Of course, you all know this. I was joking with you. So what's the physics of the Lennard-Jones potential? So the physics is at short distances, this is indeed increasing very rapidly. And at large distances, you have this negative tail that wins. So you've seen that plot hundreds of times, and that's the shape of the Lennard-Jones potential. And where is sigma? You see, this is smooth here, so sigma really means nothing. So really what I should do is I should plot R divided by sigma, and this is a number. And I should plot V divided by epsilon, and then I have taken the units out, and this is just the function that's left. So 1 over R to the 12, meaning this is really the hardcore repulsion that we need if we want to understand the physics of glassy systems, dense systems. So that's the hardcore repulsion. And this is attraction at long distance. Okay. So just to make the connections with the many things we've said before, remember I've told you about the van der Waals equation of state. So this is the attractive forces that van der Waals incorporated to the equation of state from the ideal gas, and this is what's giving rise to the liquid gas phase separation. And this is what you learn again in the first years of statistical physics. So why the Lennard-Jones potential is light? It's because it has all the physics you want in it. So if you want to look at, say, again, basic stuff, because that's a school after all. If we look at the control parameters that we have, so we have to change for instance, the temperature, so the energy scale we need to set. And the other thing we need to fix is the density, for instance, of the system. And that's the two parameters that I'm going to use. So I like to work with rescaled variables. So temperatures for the Lennard-Jones potentials will then be expressed in some units, and the units are given by the particle interaction. So when I'm going to report my simulation work, I'm going to introduce the pair potential for the Lennard-Jones, and I'm going to use this and this for the units of energy and distances. And then the density being n divided by v, it's 1 over a volume. So if I want to make it non-dimensional, I will take that number sigma out. And this is a non-dimensional density, and this is a non-dimensional temperature scale. And now anyone doing simulation in those units will find the very same phase diagram that I'm going to sketch a little bit for you. So let me do it before I get it wrong, something like this. Okay, so high temperature, low density, what we have a gas. High temperature, modest density, above the critical point, we have something that people call a fluid. High temperature, increasingly large density, we have a liquid. Okay, so the G is the gas, F is the fluid, and L is the liquid. Okay, so the fluid is when you cannot tell the difference between the gas and the liquid anymore, so you call it a fluid because it's neither a gas nor the liquid. Okay, if you go inside that thing, the system is going to phase separate between the gas and the liquid, and this is the first order transition that I have told you about, that you get from the van der Waals equation of state. And if you increase that temperature and you go back, the first order transition is going to transform into a second order critical point. And this is the critical point that we have discussed many times in those lectures when I was telling you, this liquid gas critical point. And when you're above, you see again, as I say, no difference between the gas and the liquid. So I'm just trying to reconnect with simple things that you know. So if you do the phase separation between here and here, what you have is a dense liquid, and that's the liquid, like this water that I'm drinking all the time. If you take that liquid and you compress or you decrease that temperature, what's going to happen? I already draw those lines. You have another first order transition towards a crystal. Okay, so X would be my crystal. So if you take Lindner-Jones interactions, you do your computer simulations. And maybe this is where the big man has done the first step. So the paper that's going to be celebrated next year in India by Raman with an H, I think has simulated the Lindner-Jones potential to start and open the field of, as we were discussing yesterday, of computer simulations applied to the statistical mechanics of the liquid state. And this is what Anizur Raman has done in 1964. And then I think I like this paper too, 1970. There is a paper called Phase Diagram of the Lindner-Jones Potential, and it was co-written by two French people, Lou Verlet and Jean-Pierre Hansen, who are the big molecular dynamics guys in France. They worked in Orsay, by the way. This is where they created the SICAM, etc. So there is a long history connecting France and India there. And Jean-Pierre Hansen, I like him very much because he was the supervisor of my supervisor. So he's like he's my granddad. So that's the Lindner-Jones potential. So I'm making a mistake here. I say I'm not going to tell you a lot about crystals because I hate them. So we need to go and do something to fight against the crystal. Okay, so that's what probably Raman and Hansen were finding. If you cool or compress those particles, you get easily a crystal. And we want to kill the crystal. So this is where the art of glass physics comes in. And I think maybe you have noticed that I like dates and history. So 1970s, the Hansen paper for the Lindner-Jones potential. Then people started to do computer simulations for glasses much later. Sometimes people quote some guy called Sidney Yip in the US, 1980 maybe, for computer simulations of glasses. I don't really like that paper too much. It exists, but it's not nice. Then comes the guy we discussed yesterday, Andersen with an E, so not the Anderson. And Andersen is really, I think, the guy who started to do computer simulations for glassy at, I would say, professional level. And so there is a paper by Andersen that I really like. It's 1984. So he takes the Lindner-Jones system and he's saying, I'm going to study the glass transition with it. And he does very nice, beautiful work. I mean, it's really a nice paper, but he makes one big mistake, but he knew he was doing it, is that all the time he calls the system towards the glassy state, he finds crystallites in his simulations. So everything is nice, apart from the fact that he cannot really see the glass transition. And that's 1984. I think 1987 he was doing better, and then you can imagine what's going to happen, because we have heard about this name later. 10 years after that, 1994, there is the famous Cobb-Anderson model that everyone in the room has been discussing. So that's 10 years, and the difference between this first paper with the Lindner-Jones and the Cobb-Anderson model that has become a very good model for studying the glass transition is that in the Cobb-Anderson models, you have two types of particles. You have big ones, small ones with interactions parameters that then, depends on the types of the particles. So you have AA, AB, BB interactions. So you have to put, to generalize these parameters for each triplet, for the three types of interactions you have between AA, BB, and AB. So here you see, if you look in the details of those numbers in the Coburn-Descent paper, the sigma, alpha, beta mean nothing. They don't mean diameters. The diameters don't add up to anything. It's just numbers that you tune. And that's the art of the Coburn-Descent model. They have been tuned such that it's really, really complicated, although, of course, now it's crystallizing all the time with the development of computer simulations. You take that mixtures, and what you see is a glass, because the crystal at the time was not easily detected in the simulations. And just introducing two types of particles was enough to kill the crystallization. And then, of course, the number of models that people have developed. So you can study A-B mixtures, you can study A-B-C mixtures, you choose. And then the more species you introduce, the more choices and parameters you have to control. So these are mixtures. And with mixtures, you can kill the crystallization. The other type of model that people use is, and it came probably a bit later, is if you have continuous polydispersity. And so you're saying, I introduce a continuous distribution for those parameters. So for instance, you say sigma is distributed according to a distribution. And you say, I'm going to, each particle will be characterized by a given sigma, and then you have a continuous distribution of sigma, and that is meant to be perhaps a good model to represent the physics of colloidal particles. When you make colloidals in the lab, I think it's really complicated to have them exactly the same size. You have a distribution of particle sizes, and that's a good way to represent those systems, etc. And the list of models is infinite. Okay? Although probably you can count them, but it's still very large. Okay? And so what is it? What does it mean that you're killing the crystal? It means that the phase diagram becomes something like this. So that, of course, that critical point in the gas and the liquid and the fluid, and the critical point, they don't go away easily. There is no reason for this. But instead of having a crystallization, what you have is you have a glassy phase when you plot T and rho in a cube. Okay, what you have is you have a transition between a liquid and a glass by increasing the density or by decreasing the temperature. This is when the system gets crowded, slow motion, all the glass physics is there. Okay, so that's the setup. So it's still a complicated phase diagram that you can easily explore. So I like simpler models. I'm giving you two because people really use it. So this is nice. You can do everything, but you can do too many things. If you want to study the glass transition, why would you care about the other features of the phase diagram? So simpler things that people have invented. And I'm not sure why people stick to the Coburn-Descent at the end, because these simpler approaches have the exact same physics, but they are way more efficient to simulate, but it's your choice. Okay? So one simpler thing is to define a potential like this. So it's looking like the Lennard-Jones potential, but then what you have is the first term you keep, but the second term with the attraction between the particle, you don't keep, you kill it, you say, I don't care. Okay? So it's the repulsive part you get, and why is it important to keep the repulsive part? It means particle cannot easily interpenetrate. That's the whole point of becoming glassy. It means I don't have space enough for myself when the density or the temperature gets low, and then glass physics essentially is controlled by this. And the attractive forces, in a sense, are decorations giving rise to the liquid and the criticality. So it's interesting from the point of view of this part of the phase diagram. If you don't care about it, just remove it. And then you have, pair potential that decays very quickly in our space, so you can, numerically integrate the forces up down to a much smaller distance. Way more efficient is one thing, and you kill the physics. If you're too close to here, you'll have density fluctuations. You never know where you are in the phase diagram. Everything becomes so much simpler with soft repulsive spheres. Okay, that's the name of that model. And the second simplification, which is even nicer, is that if you think about the control parameters of that system, in the Lennard-Jones system, you had epsilon and sigma that were tuning the density and the temperature. If you think 2 seconds about how the system thinks about epsilon and sigma, they appear as a product here, so they cannot be varied independently. Instead, it's just the product of these two guys that matters. It means that instead of controlling independently the density of the temperature, you can't. Changing one is equivalent to changing the other. So it means the phase diagram is just one-dimensional. Okay, so you don't have 2 control parameters to worry about. You just have one, which is either temperature or density. You decide it's equivalent. Think about it by yourself on your piece of paper if you want. And so people in that field have introduced a way to introduce a control parameter that is capturing that thing. So it means if you define that control parameter gamma, you realize that changing rho or changing t, it's strictly equivalent. So we call it gamma. And when I say the phase diagram is one-dimensional, it means you can just plot things as a function of gamma. Or maybe there is a increasing rho is like decreasing t. I think there is a minus, which is wrong in my notes, by the way. Okay. Which is such that increasing gamma, it's like increasing rho or decreasing the temperature. And so if you work hard enough, you have your binary mixtures of source spheres, you increase gamma, and you are left with a fluid to glass phase transition as you increase that one-dimensional parameter. So it's way simpler than this. You've killed the crystal, you've killed the thing, and you can study the glass transition very, very simply with this model. So I like it very much. Sorry?
Is the power here important or any number?
No, it's just the convention. So again, history, I like it. Lennard-Jones, he was like the head of the chemistry department in Cambridge, so you see his pictures all over the walls over there. So he invented the Lennard-Jones potentials by thinking about your question. So he said, one thing I know is that you have attraction and repulsion in liquids. The attraction we know because it has a physical interpretation. It's dipole-dipole fluctuation. So to the 1 over r to the 6, this one you cannot play with it because it comes from quantum mechanics. The 1 over r to the 12 has no explanation whatsoever in the context of classical. I mean, we know why, but in terms of modeling it with 1 over r to the 12, no reason whatsoever. So what Lennard-Jones did is he defined a certain power, minus r to the minus 6, and then he played with this, and he looked at experimental data on real liquids, and he found that 12 was fitting better most of the liquids, and so he decided 12. And so there is a certain symmetry between the 12 and the 6 that I think looks nice. If you take 13 and 6, it looks ugly, perhaps, but no good reason beyond this. So indeed, I mean, you could take an N and decide how soft or how non-soft, and people have played with it, asking different questions about the influence of softness, for instance. Okay. But the simplest of the simplest is the one that I prefer. It's, of course, the hard sphere system. Okay, so hard spheres also are simpler for many, many reasons. So you know the hard sphere potential. It's the one that, the potential is infinite here, and then it's 0 for r larger than sigma. So that's the shape of the hard sphere potential. So what's nice with the hard sphere potential it keeps a number, sigma, that this time, yes, I agree with you, can be interpreted as a physical diameter. It means two particles don't interact up until they touch, and then the potential gets infinite. So it has the flavor of a diameter, although it's still as wrong. It's still point particles, but you can think about it as a diameter a bit more easily. Even though when you take mixtures and you make them non-additive, like in the carbon descent, it's not a diameter anymore. So, sorry, but hard spheres don't have a diameter. They have a sigma in the pair potential, but they are point-like particles. Okay. So what is really cool is that if you want to represent or think of the phase diagram, so you still have your sigma, so you can still define the density or the rescale density. And let me go there before. So I was using rho times sigma cube as a rescale density before. So for hard sphere, people define something that they call the packing fraction. I always get the prefactors wrong. It's pi divided by 6, rho times sigma cube. So instead of working with this, you add the pi divided by 6. And why is it good? It's because it's really the volume occupied by the particles, with the 4/3 pi r squared cube divided by the total volume. Okay, so this is the packing fraction. You define as the volume occupied by the particles divided by the total volume. So that goes into n particles divided by v. You have the density. The sigma cube comes from the volume, and this is the prefactors for the volume of the spheres. But you see, in terms of what I was saying before, phi is just, again, the rescale density of the Lennard-Jones system. It's a way to make the density non-dimensional. And if you think of, I have real objects that are really hard, like these granular systems that I've seen in your lab, for instance, they really have a diameter, and this is really the packing fraction for those particles. But in computer simulations, it's a bit more abstract, perhaps. And then the reason we like it, so you have your density, but now think about changing the temperature of that system. Against what quantity do you define the temperature? Well, you don't have one because you don't have an epsilon anymore. So you can take t equals 1, 10, 100, 1000 in your simulations. Doesn't matter. Against infinity, it's always finite. Okay, so temperature plays no role. The absolute value of t plays no role, I should say. Plays no role. So when you look at hard sphere papers, they say, oh, we take t equals to 1, and then t disappears from all the expressions. That's not quite true. What they really do is they non-dimensionalize everything by kBt, if you wish, and then you work in those non-dimensional units. Okay? So because you have one control parameter, which is the density, or the rescale density, again, you have a fluid and you have a glass, and your phase diagram is one-dimensional, the forces extends to sigma and then becomes 0. So in terms of integrating, the equations of motion, it's way, way simpler. And I like them very much. And all of them, I should say, and should be very clear for you. I mean, they're all, to me, they're all the same. We call them different things, but in terms of the physics they display, it's equivalent. I show you correlation functions for 1, 2, 3, 4, 5, 10 models. You can tell. Okay, so physically, they're all very good models to describe the glass transitions. So really, choosing a model is your choice. So I go for simplicity and efficiency rather than, habits. So dynamics. So we specified how the particles live in continuous space. They have positions, momenta. If we want to study the glass transition, we have to specify a little bit about the dynamics. I'm trying to look at the clock. I want to finish on time. So if we want to study and do molecular dynamics like the venerable people we mentioned, so for atoms and molecules, what we use as dynamics is simply Newton's equations, right? So we have classical interactions for the classical equations of motion, Newton's equations of motion. And that's it. You don't think too hard about it. You just write it down. For all the particles, what you have to do, is you have to define the positions, and you take the second derivative, and you say it's the sum of the forces dv, dri, j over that's it. So you solve this, and you have to give yourself initial conditions. So it's second order equations. You need all the velocities at time 0. You need all the positions at time 0. And that's it. The problem is well posed. You know, you have your initial conditions for the velocities and the positions, and you integrate this, and that's it. You have solved the problem totally. So that's it. You solve this, and you are done. So that's why it's so easy. Okay, and excellent textbooks that teach you how to think and understand the subtleties of how to integrate the equations of motion. But you know, conceptually, it's very easy. The rest is just technical details. So, many problems to solve. The textbooks are really excellent. So you need to discretize these equations. Okay. So people have worked hard to understand what's the best way to discretize Newton's equations, how to integrate, how do you make reversibility, how do you store, it's all in the books. You have to think about efficiency. Okay. So each particle is interacting with everybody. So in principle, each time you want to integrate the equation of motion for particle I, you should sum over all the particles surrounding in the box surrounding particle I. But of course, if the pair potential is very short, one particle is going to interact with 3 guys and not with n guys. You know, this is where the art of simulation comes in. How do you truncate your interactions and you make a very efficient integrations of the equations of motion? You have to think about the fact that the system is finite, so you take periodic boundary conditions. You are used to, those kinds of things. So I go very, very fast. A bit more subtle, perhaps, and people maybe sometimes don't remember. You now need to control, your thermodynamic parameters. Density is fine. Density is just how many particles you have put in your simulation box of size L, so the volume is L cubed, so density is easy to control. I can change or, Temperature is a bit more complicated because temperature doesn't appear in these equations. I'm just solving Newton's equations, and I know that Newton's equations conserve the total energy, so total energy being kinetic plus potential. Where is the temperature? It's in the kinetic part. So how do you control it? It is an art. So controlling T, you need thermostats. So it means you need to couple your particle to some bath, and again, textbooks tell you how to do it. It's been worked out. One of the big names in thermostatic computer simulations is Hans Andersen with an E, the same Andersen as before. He thought a lot about how you impose pressure temperatures in computer simulation, and he was one of the first guys deriving things elegantly and systematically. So Andersen is really an important person for that field who did very nice things. So controlling your, I say temperature, but it could be pressure, chemical potential. All this is in the textbooks, well understood. So I mentioned that Andersen paper 1984. I like it. So if you read it, he's really describing what can we do with computer simulations to understand the glass transition. And at the time, they were simulating 500 Lennard-Jones particles. Okay, so if you go back in time and you go to the famous molecular dynamics paper just after World War II, they were simulating 32 particles. So at this time, 500 was really a decent number. And they give number in the paper that I haven't read again. They say we can do 100 time step, so discretization steps per minute. And he was working, I forgot, Stanford. So probably he had decently big computers at the time. So I made the calculation once with what we can do now. So what we can do, so in my, in my computer, we have a limit, so you cannot run jobs that last more than 2 weeks. So people have adjusted to the 2-week limit. It's just giving you, So in 2 weeks, we can do 10 to the 9, roughly, time steps. And so if you make the calculation, I did it, it means we've multiplied how many steps we can do in a given time unit. We've multiplied by 1,000, 10 to the 4, something like this. And it's all due to progress in hardware. This is how faster the computers have become since the early times of Anderson. So this is roughly what we can do, integrating the Newton's equation 10 to the 9 times in about 2 weeks, which is the time it takes to finish your project. And you can do 2 months or 2 years, but then it's getting very, very long. So I think 2 weeks is a good unit of time to think about CPU time. 1 sec, yes?
The hard sphere potential, how would you simulate that? Because that's an infinity and computers cannot handle it.
Okay, so the first paper who reported molecular dynamics simulations was for hard spheres. So the very first time someone thought about doing computer simulations for particles was for hard spheres. So you can imagine that the problem has been understood, So how do you do in practice? It's true, if you just discretize your space and you go continuously there, then you have a problem because you have nothing and suddenly you have infinity. So it's really hard to discretize. So in practice, for hard spheres, that's not how you do your molecular dynamics. So if particles have a velocity and they approach each other, the velocities are constant because they don't interact up until they touch. And then you have a collision, and it's an elastic collision, so you go back like this. So what these people did, and that's why they started with hard spheres, they didn't need to really discretize Newton's equation. They needed to think about collisions. So you have your systems, and the next step is when the next collision is going to happen. So you go to the next collision, you make the collision, and that's it. You've made your collisions by thinking about the collision. You advance the time step to there. And then you say, okay, what is the next collision is going to take place here? So I advance the time up until those 2 particles collide. I do the collision, I go to the next. And it's a collision-driven molecular dynamics for hard spheres, if you wish. And it's way simpler. You just go from one collision to the next. Good point. So, so I was thinking about problems, discretized, So the biggest problem, and I had that question before, when we look at liquids that become very slow and the dynamics is very slow and you want to maintain equilibrium, but the time scales are growing so big that they start to compete with your simulation time. So thinking about how do you test equilibration in glass-forming system, it's not easy. And even though the models are good, you should remember that at each time step you should should make sure that the system has not crystallized, otherwise I don't study the right physics. And all these things have well understood. Okay, so I think I forgot to finish. I thought I had something to say in addition to this. So if you think about the number of time steps that we are making, so I said, in a reasonable of time, you make 10 to the 9 steps, integrating these equations that I have written down. If you want to make a careful job of integrating them, you have to take a discretization of time that's a bit, smaller. So typically, in rescale time units, it's about 10 to the minus 2, 10 to the minus 3. People, need to learn how to fix that thing. Let's say you discretize in your time units for the Lennard-Jones. 10 to the minus 2. So you have your delta t to integrate your equations, which is 10 to the minus 2 in your time unit. But you can do 10 to the 9 steps. So it means you can go up to 10 to the 7 in your time units, okay, roughly speaking. So what can you accomplish when you can integrate up to 10 to the 7 tau 0 your time unit? Well, remember what I said about the glass transition, it starts with microscopic times of the picosecond, and then it shoots up, and you would like to study 10 to the 12 orders of magnitude of glasses slowing down. So clearly, here you can simulate 10 to the 7. But when we do statistical physics, we don't just want to go to that time. We want to equilibrate the system and, measure stuff, thermodynamics. We want to sample enough configurations weighted by the Boltzmann distribution to compute, say, correlation functions, density fluctuations, whatever. So a decent sampling would be, I have to record about 100 configurations so that my average is good. So it means you're losing, 100 of these just to store configurations that are independent. You're limited by your discretization. At the end of the day, what you can do is you can reach to alpha, which are about 10 to the, so I say 10 to the 7, but I need 100, so it's 10 to the 5, okay? So that's about from 1 to 10 to the 5, that's about the increase of the relaxation time that you can decently simulate if you want to have good statistics. So it means you can simulate about 5 orders of magnitude of the glassy dynamics in those computers in those reasonable amount of time. So you're missing 7 orders of magnitude compared to experiment, and 7 is a good number to remember. That's what you have to do if you wanted to claim I have done computer simulations that are relevant for experiments. So it's a factor 10 to the 7 compared to the increase that you've made in 35 years, which is 10 to the 3, so it's going to take a while to get there, right? So other dynamics compared to Newton's equations have been introduced, thinking in particular about, again, colloidal experiments, so I like at least to write down these equations. So if you think about my particles are colloids and they are immersed in a solvent and they are colliding with small molecules, with many of them, and I have viscous damping from my solvent, you go to the Langevin description of the particle, and I'm just writing it both as a recap and also to go towards colloidal physics, and to make a very important point at the end. So that's a multi. Okay, so I write down the full Langevin equation. That again, Langevin, 1905. So it's another historic chapter that's very nice, but not today. So thinking about big particles in a solvent, you have the viscous damping. If I drag a big particles in a solvent, I have a force that resists, that's inversely related to the velocity of the particle, that's the viscous drag. And what you have is you have the noise which is setting the thermal fluctuations in the system. So that's viscous, or the Stokes drag. And you have the force, and if those two things are well related, then you have equilibrium dynamics. And because, again, that was mentioned in the other lectures, you have a Gaussian noise with uncorrelated everything, and the strength of the noise is given by 2 times the temperature times the viscous damping times delta functions. Okay, so uncorrelated white noise. And people can use these dynamics to, for instance, understand the physics of colloidal particles. So one dynamics that we also like to use, if you think that your colloidal particles are bigger, 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 and bigger, and you have these big things that you can see in the confocal microscope, then at some point the inertia of those particles is going to be become very irrelevant, and then you simulate what you call the overdamp limit, and it's really the same equation where you kill the mass term, and you just have velocity is the force plus the noise, and this is called the overdamp limit for very big colloids. Okay, so you can do your computer simulations in this way if you prefer, and you think that you're not simulating molecules or atoms, but bigger particles in the solvent. And then one dynamics that I really like, so that was another dynamics, a third dynamics, and this is becoming more and more abstract. This is the Monte Carlo way of doing simulations. Okay. And you forget about the continuous time, you forget about physical equations of motion that I think the particles are obeying. Now it's your choice. You decide how to simulate the dynamics of these particles, and you say, oh, I learned from the tools of statistical physics, again, where Monte Carlo simulations were invented, and I learned how to do it. So what you do, again, in 1 second, Monte Carlo simulations, and you've heard those words in the other classes. It's a Markov chain, so you go from one state to another, to another, to another, without any memory. So that's a Markov process. So you invent a Markov process, and you are clever enough that it's going to equilibrate the system. Okay, and the primary goal of Monte Carlo simulations in statistical physics is devise a tool, an algorithm, with no physics in mind. You make a Markov sequence of events in your system such that at the end of the day, you know that your configurations will be representative of the Boltzmann distribution. So it's a tool, it's an algorithm, which is invented to sample the Boltzmann distribution. Okay, and that has been used even before molecular dynamics. That was invented way before that. Okay, so it's a tool, it's a trick. There is no dynamics here. It's just a sampling method to solve for the partition function of the Ising model, for instance. That's how it was devised. But of course, in the course of your Markov process, the particles are going to move, and there will be some dynamics attached to these things. So what's the simplest way of doing Monte Carlo simulations for your system? And the very first paper who did that, again, used hard spheres. The same person who invented the molecular dynamics, Bernd Yelder, was there already at the time to invent also Monte Carlo simulations. And what they do in terms of moving the particles is I have to invent discrete moves of the particles. So what they did is they said, I take one of these hard spheres, I try to move it a little bit by a given distance. If it doesn't jump onto another particle, it's an equally good configuration. So I'm going to move my particle. And that's one step. And in case you want to make a displacement that is violating the hard sphere constraint, you reject that move, and you go to the next one, and to the next one, and to the next one. So this is a Markov chain, because to make one step, you don't need to know what happened in the past, so you forget about the past. And it's a discrete time thing for moving the particles around. The only thing you know when you do this algorithm is that at the end of the day, if you do your measurements, they will be correct, and you will sample the Boltzmann, the equilibrium distribution. And that's the field of Monte Carlo simulations for you in 3 minutes. Okay, so now that the particles start to move around in your lattice, you can measure how fast they move, the mean square displacement, your time correlation functions, you name it. You can do this with the overdamp limit, you can do this with Langevin, you can do it with Newtonian. If your pair potential is the same, it's say the Lennard-Jones and the hard spheres, you have 4 ways of simulating or accessing doing computer simulations to understand the physics of one model. But now you have 4 dynamics, and this is where I think I wanted to go with my next point, that it's not obvious, but it's a result, and it comes from the physics of the system. Okay, so I measure using molecular dynamics my relaxation time to alpha for my particles. I just do this, I do this, I do my Monte Carlo algorithm for the same system. I compare the temperature dependence of how these things are growing as the temperature decreases. And the strong result is you do your molecular dynamics, you do your Langevin dynamics, you do your Brownian dynamics or overdamp dynamics, you do your Monte Carlo dynamics, and you plot them on top of each other, and they all look the same. Okay? And typically, the way the system is slowing down, the way the physical dynamics, the glassy dynamics sets in as you decrease the temperature, Essentially, it doesn't care about what algorithm or equation of motion you've used. Whatever you do, you'll find similar glassy dynamics, and you'll find something like this. You'll measure your relaxation time. You'll measure something that's looking like an Arrhenius, that's looking like, super Arrhenius if your model is good enough. You will have your 1 over the onset. Typically, when you do computer simulations, your time here is essentially the macroscopic time scale of your system or your Lennard-Jones time scale. It's about 1 in reduced units. Here you have the high temperature liquid, and I said if that guy is 1, that guy will be 10 to the 5 to Lennard-Jones, for instance. And that's about what you can do, and you can do it with Langevin, Brownian, Monte Carlo. You're going to rescale your things, and they all will be similarly looking, and all the data will have the same shape independently of the model. And that's a strong result. It could have been that the way you do your integrations of the equations of motion matters for the physics. It doesn't. So as usual, when you find something like this, you have to think, is it good or is it bad that those dynamics give you the same result? Well, it's good for many reasons. First of all, because you have many ways of doing the same thing, then you should go for the most efficient one as usual. And there are some of them that I really hate because it's such a pain to do. There are some of them that are very easy to code and are extremely efficient. So in terms of doing in practice the computer simulations, go for the faster, the simplest one to code and everything. And then anyway, the result doesn't depend on how you chose to do your simulation. So that can be seen as a good result. I had a second positive thing to say about that, but I forgot. Why is it interesting, Pinaki? I forgot. It is interesting. Okay. The other thing I wanted to say is that if the glassy dynamics of the model you want to study is extremely robust and universal against the details of the macroscopic equations of motion, I'm confused. I mean, I had the idea, start the sentence, and I forget the idea. It hopefully means that the details of the glassy dynamics don't depend on how you choose to simulate them. So it means change the model, change the dynamic, change everything. Anyway, the physics is super robust, and it's about the same. You look at the details, for instance, of the dynamic heterogeneity in real space. In those different types of dynamics, it doesn't matter whether you have inertia, viscous damping, or even stupid Monte Carlo moves. The way the particles move at long time, it's fairly universal. And it doesn't remember how the particles were moving in the first place. Meaning, when you do colloidal experiments and molecular experiments, there is a good reason to say, yes, this is relevant. We are doing the same physics, which was not obvious at all, after all. It could be that colloids slow down in one way and molecules in another, and your colloidal experimental physics are just a different field. But no, they are the same field. So that's the positive way of things. The negative side of it is that if you do computer simulations and you want to study the statistical mechanics of liquids, if you use one of those algorithms, it's going to slow down just as fast as the physical dynamics is slowing down. So it's good, you can study the dynamics, but in terms of speed up and equilibrating and really understanding the equilibrium properties of those systems, it's bad because then you have a slowing down of your computer simulations that's unavoidable. So if you want to do simulation, this is bad. And that, I think, is what the swap Monte Carlo algorithm is about. Okay, so I'm telling you, you do those algorithms, you can go to equilibrium, but the time it takes to go to equilibrium is dictated by the physical glassy dynamics. So you can study the glassy dynamics, but it's becoming very slow. So it's interesting to understand the dynamics. It's bad for the CPU time that you are spending in equilibrium, in equilibrating your system. So I go back to this, and again, I'm trying to make the story as fast as I can. So I've tried to explain Monte Carlo simulations were invented as like an algorithm, something totally unphysical, with one goal in mind. I want to go and equilibrate the system. In principle, when you invent an algorithm, you want to be as fast as possible. So you invent something, you construct an algorithm, you make sure that it's going towards equilibrium, and then you can sample the Boltzmann distribution in some way. So that's a tool, that's a trick. It's a black box. It's an algorithm, if you wish. So Bernie Elder and company said, one way to do Monte Carlo simulations of particles is just pick particles one by one, move them a little bit, and then you pick another one, move them a little bit, and you move all the particles around. And you find your Monte Carlo dynamics that is essentially reproducing thermal dynamics. But that was Bernie Elder's choice, after all. He could have done something different. He could have said many different things. He could have said, I'm going to consider triplets of particles, and I'm going to do something very complicated with it. Provided my algorithm is well constructed, I am guaranteed that I'm going to equilibrate the system. So, the choice of Monte Carlo moves that you make, it's really it's your black box, it's your algorithm. And if you could invent a way to, I moved all the particles, I put them back in the box, and poof, in one step, I'm in equilibrium, as someone, I think, asked me in the corridor one day, you would be God, because you would be able to sample the Boltzmann distribution in one go. And then there will be no slow dynamics. The time scale to go and simulate the system would be 1. Each time I sample something, I have an equilibrium distribution. That's the dream of all people doing computer simulations, being able in one go, I put the particles, it's an equilibrium configuration. I should be fast, but I opened that parenthesis. This is what the machine learning people want to sell us. They want to say, we are going to invent a Monte Carlo, machine learning assisted Monte Carlo algorithm. There are so many people who are trying to do it at the moment. And they are going to say, we start from, whatever, simple, I put my particles and I invent an algorithm, and the end of the algorithm is one configuration that I detect and produce in one go that is representative of the Boltzmann distribution. And this is what these generative models for, statistical physics are all about. And the analogy that you all know from the field of machine learning is, how do you produce fake images? How do they do it in practice? They produce an image that's just gray, random noise, and they have a machine that transforms this into your face. And that's these generative models, and they produce faces out of noise in one go. So this is what statistical physicists would like to do. I give you, I put the particles in the box randomly. I invent a tool, a black box, machine learning assisted box that is going to transform this into an equilibrium configuration of the system. And you may have seen, or you may not have seen, but this is like a very active field. The attempts I know so far for glasses, 0 success, right? So it means this is a difficult problem, we know. So being able to sample in one go glassy configurations, maybe in 2 years, 1 year, 6 months, 10 years, never, who knows, will be doable, but I think it's an interesting challenge. And among the many problems that we face in computer simulations of statistical physics models, probably glassy systems will be like the hard test. If you can predict this one and sample this very quickly, I'll be impressed. Some models, the Ising model, it's done, but the complex systems, it's not done. It's a very big challenge, I think, and people are excited about it. I close this one. So being 1 and not feeling the slowing down, it's like the target. You would be able to sample very, very quickly the physics of glasses down to arbitrarily low temperatures, and you would solve the problem. You would go to the Kurtzman transition, measure all the things we have discussed, and you would essentially answer the problem directly, because it would cost you 0 to sample the Boltzmann distribution across the phase transition. You would be able to study it directly. That would be great. Okay. So we are not yet there. So the question is, can you do better than the physical dynamics? So the dream is to be at 1. And of course, doing better is what this algorithm is about. So the algorithm is like this, is in addition to your physical dynamics, okay, so the dynamics that you know is slowing down dramatically. So whatever you're doing whatever dynamics you like. This is your physical dynamics. You stop and you do the following Monte Carlo steps that you invent out of this, and you do swap Monte Carlo moves. And the Monte Carlo moves in the swap Monte Carlo algorithm are super simple. And instead of choosing 1 particle and moving it, you choose 2 particles at random. Okay, so I go back to my cartoon and I make it a bit clearer so that, okay, so this is my Cobb-Anderson binary mixtures of A and B particles. So what I do in this swap Monte Carlo move, I choose 2 particles at random. And the 2 particles need to be of different types. Okay? If I choose 2 particles which are the same, I will do nothing. So I choose 2 particles at random. For instance, in this example, a small one and a big one. I swap them, so I swap their position. So the Monte Carlo move that I propose is I'm trying to put that guy over there, and I'm trying to put that guy over here. So I'm swapping the position of those 2 particles. And then I need to be careful that I satisfy all the rules to construct a good Monte Carlo algorithm. So I need to satisfy what's called detail balance and everything, I make sure that my algorithm here works well, and that's it. So I accept or reject these swap moves according to the Monte Carlo rules, and that's it. And you do it again, you do many, many times, and then you go back to your physical dynamics, then you stop, you do many of these swap moves, and so you add these swap Monte Carlo moves to your dynamics, and that's it. So that is the algorithm. So in that sense, it's a black box. You do stupid things that you invent and you decide and you say, if I do my algorithm very well, I'm guaranteed to reach the Boltzmann distribution because it satisfies the detail balance. The question is, how long does it take to reach equilibration compared to the physical dynamics? And this is where the swap is really looking good. And the reason it's looking good, it's looking so good that I need to extend that thing by orders of magnitude, right? So I say this is the physical dynamic. It slows down after 10 to the 5. It's the 2 weeks of CPU time, and you're dead. So you do your tau alpha MC swap. Then let me call it like this. So that's the swap. And the white was the tau alpha for my favorite physical dynamics. Okay. So that's my physical dynamic. So you do the swap, you compare, and you look, and you see something like this. I'm going to do one more thing before, just to be sure. So if I could do simulations for 10 to the 7 times slower, so 10 to the 7 times 2 weeks, I would reach 10 to the 12, and that would be somewhere here. That would be the definition of the experimental glass transition in those units. That would be the 12 orders of magnitude that you would like to cover to reach TG. But you cannot do this easily. So So what the swap is doing for the most models that we have been able to invent is to remain relatively okay at TG and stop here. Okay. So that's the time it takes for your Monte Carlo algorithm to reach thermal equilibrium roughly. And so for the optimized models that we have, again, I'm making the story a bit short. When you reach that temperature where you believe the physical dynamics would take 10 to the 12 in your Lennard-Jones units, for one prototypical model that we have of soft repulsive spheres, the relaxation time to the equilibration time for the swap algorithm is about 10 to the 2, meaning the speed up in terms of how long it takes to reach equilibrium at this temperature. It's a factor 10 to the 10. Okay, so by the time your algorithm with the physical dynamics are extremely frozen, would take forever to reach the glass transition, the swap is not yet super slow. So it means, in half a day or in 1 minute on your computer, you produce at this temperature where the physical dynamics is totally dead and would take you 10 to the 7 weeks to reach equilibration. You do it in 1 second on your computer. So that's the speed up. And then eventually the Monte Carlo algorithm swap slows down and then reaches the CPU limit. And this is the temperature where the swap simulations then fall out of equilibrium. And then it means the speed up at this temperature would be much larger than 10 to the 10, but it's even more difficult to estimate. So that's the magic of the swap. It is a Monte Carlo algorithm. It's not, it's not reaching the, like the dream that I was discussing before, finding an algorithm that's totally insensitive to the slowing down and the fact that you are at low temperature. So it goes, it's almost like a dream, the swap at TG, but finally it stops and it slows down itself. It has trouble finding equilibrium. And in your 2 weeks below that temperature, you cannot equilibrate the system anymore. So that's the deviations from the dream, if you wish. But this is the speed up compared to the previous algorithms. So that's the swap Monte Carlo in a few minutes. What is it giving you then? I'm finishing on this, and then I take your question. So why is it useful? It's useful for at least 3 reasons. So it means you can study equilibrium properties and stay on the liquid equilibrium line down to temperatures that are below the glass transition of the experimental system. So it means you have moved the way, the temperature regime that you can access with computer simulation from here to here, from way above the glass transition to way below the glass transition. So it means you can at least understand or study, analyze, measure equilibrium properties, static properties of your system down to very low temperature. The second thing that we think is very nice is you can then equilibrate your system here, 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 at very different initial preparation temperatures. So we are using it in a sense to vary the stability of computer-generated glasses over a gigantic range. We can prepare extremely poorly annealed systems, good systems, experimental systems, and better than experimental systems. And we can see whether, when we go into the glassy, into the solid, whether that has a strong, medium, or zero impact on the physical properties. So that's giving us a new way to understand what's the physics of low temperature glasses by having this new control parameter. And the one thing that we do is we use that to understand the dynamics a little bit. So I told you when you do swap, you're doing stupid and physical moves, so you cannot use the swap itself to understand the glassy dynamics. But what you can do is you can do the following thing that we are using a lot these days. You can use the swap to go to this temperature where it's really terribly complicated to equilibrate with the molecular dynamics. And in 1 second, the swap is giving you an equilibrium configuration at this very, very low temperature. Once you have these equilibrium configurations, you can have an initial condition. That's good. Okay. And so what you can do now is you can launch a molecular dynamic simulation from that one configuration that you have prepared. And so you launch, an MD or an MD simulation. And because you have equilibrated the system, you are guaranteed that that trajectory will be representative of thermal equilibrium at this temperature. And so that trajectory, by brute force simulations, you will not be able to generate because you will never have that initial condition. But the swap is giving it to you. So now you can use your entire simulation time, your 2 weeks of CPU time, if you wait, to generate a very long trajectory. So what I said is that we can do 10 to the 9 steps, which means 10 to the 7 in, Lennard-Jones times, to Lennard-Jones. And that's about what you get in 2 weeks, but you get 10 to the 7, Lennard-Jones times that are useful for the glassy dynamics. So instead, before I was stopping at some time, so the speed up we get overall when we look at this, and we transform this into physical units for molecules. So we have moved the boundary of what we can do for the dynamics, and we have a paper that has this title, to about 30 milliseconds. So remember, 10 to the 2 second is the glass transition. Microsecond is roughly where the simulation was stopping before. So we have pushed by this tool molecular dynamics simulations up to about 30 milliseconds in physical time. So in a sense, before we were stuck there, now we can generate conditions there, and we can roughly study dynamics about halfway between where we were before and where we would like to go to represent the physics of molecules near TG. I don't remember who you had the question.
So for the Markov chain simulations, the tau alpha is basically given by the inverse of the second largest magnitude. So
You could say that.
So is there any sort of mathematical reason why it should always diverge with increasing beta? Like, at least for these 2 cases that we know, sort of increasing beta is, I guess, related to how asymmetric the Markov matrix is.
So everything you said is correct. It's just that in practice, if I could, using that matrix diagonalization of the Markov matrix, if I could do it for even the physical system and the physics, then I would be able to predict the relaxation time of a supercool liquid. And I've told you in the many lectures before, that's a complicated problem. Nobody knows how to do it. And in particular, if you could do that calculation, even for the physical moves, you would be God. You would have solved the glass transition problem. And so you're asking me, can you do it for that more complicated dynamics? I can do even less. Okay? Yes?
I'm asking whether the Square Monte Carlo algorithm is will be useful in case of non-equilibrium models where in steady state the Boltzmann distribution is not satisfied.
Well, so it's a generic question that you could say. So open a book on Monte Carlo simulations. You open any books, the Frankel-Smith, like the Bible of Monte Carlo simulations in statistical physics. You have, 30 very clever methods to simulate phase transitions, chemical potential, Every single one of them is dead when you go out of equilibrium. So all the algorithms and tools and methods and super tricky things that people have invented to do Monte Carlo simulations, study phase transitions, every single one of them falls down, breaks down if you go to a non-equilibrium steady state, because the way this algorithm works is by starting, and it's very clear in the Frankel-Smith book on Monte Carlo simulations of liquids. He say, oh, let's do that problem, and then he say statistical mechanics justification of the algorithm. It always starts by rewriting one way or the other the partition function with the Boltzmann distribution there. So most of them, you open the book. If you want to do physics out of equilibrium, you take that book, you put it in the trash. It's useless for you. the swap is useless for you as well. It's a good book, so you should keep it, but it's a metaphor. At the back, maybe?
How do you say configuration is from equilibrium? I mean, after doing this, how do you ensure that it's equilibrated?
So there are two questions in your question. I detect two questions in your questions. First of all, the question you're asking in general, you can ask it for the physical dynamics. Well, how do you know you're in equilibrium? And that's one of the stars that I had when I say, let's list all the potential problems in the simulations. How to make sure that you're in equilibrium is one of the problems that you have to solve. If you know and you're confident, you know how to solve it for your molecular dynamics, your Langevin dynamics, your physical dynamics. It's the same type of problem. It's not more complicated, but it's not easier. It's the same problem. It's the same question. And that question you can ask this time to anyone doing computer simulations. How do you know you've done a good job? So your job is to convince the reader or the referee when you publish a paper. But for the swap, it's not more difficult. It's not easier. It's just the exact same task. So we can talk about the task, but I don't have time in the lectures. But the swap by itself doesn't introduce more complications. That's what I wanted to say.
Is this swap is model independent? So
It is not. So just like the algorithms invented to solve, the slowing down near phase transitions, the algorithms were good. They are good for one case. They are not good for another. And usually, if you want to invent something that's not just the simple physical dynamics, you have to think a little bit, you have to optimize a little bit, and the optimization depends on the model. And since the first time we saw this, I think we've worked hard on this problem, so I can tell you maybe on the side what the progress we've done. But yes, for some models, it's trivial that the swap will not work. So imagine that you have a model where you have gigantic particles and super small ones. And the swap move is I take the small one, I put it there. It has a big room. I try to put the big one in the room occupied by the small one. It's going to be rejected, so the algorithm will be very inefficient. And so I think our job as people inventing algorithms, for instance, would be to think about that and try to make it as universal, model independent as possible. But that's what we can do and say. My goodness. Okay. I wanted to say the following. I wanted to use that thing to close and revisit extremely quickly in the last 10 minutes what we have been saying about the lattice models and the mean field theory. And using this one thing, the fact that now with the swap algorithm, if I'm not interested in the dynamics, and I'm very interested in the dynamics, I'm thinking about all these features that we've discussed for the mean field theory of the glass transition. One of the cool things that the swap is giving us is like this new temperature regime that we can now access. And even though we cannot study the physical dynamics to arbitrarily low temperatures, the thermodynamics, the correlation functions in space, the entropy, we can measure everything. And that's what has occupied us a little bit. Okay, so let me go as fast as I can, and then I stop there. Okay, so I've told you one of the key things that is being predicted by the mean field theory is this configurational entropy. And so now that we have access to these low temperature configurations nearly for free, then we can revisit those measurements. And so how to measure the configurational entropy in simulations. I wanted to explain this, but I'm a little bit short of time, so I'll do two things. The first thing I will do is, this was the core of lectures that I was invited to give in 2018, I think. So there are, I think, YouTube recordings of those lectures somewhere. They exist. And out of these lectures that I have polished a little bit, I was mentioning at the coffee break, We wrote a short paper about this method. So there is a paper in the Journal of Chemical Physics, je sais plus, 2019 maybe. I think I didn't put it in the references, but the title is Configurational Entropy in Supercooled Liquids. You know, it's a stupid title like this. And it's going over all the different kinds of methods that, you know, people have invented to study the configurational entropy. And I won't go over them now, but there are at least 3 different kinds of extremely robust and physical methods that we have used. So there are 3 methods that are based, one, on I'm going to explore the properties of what's so-called the potential energy landscape. And I mentioned this word for 2 reasons. That method has been invented way, way back in the year 2000s, and that's the method that Shrikant Sastry has used a lot in his prime youth when he was a postdoc to probe and measure the configurational entropy in supercooled liquids. That method still exists, is valid, and we have revisited it, and that's the Sastry approach to this. One method that we learned from the book I was mentioning before. So Dan Frankel is the author of the book that you should not throw in the trash. So the Frankel lab method, it's one of the very cool algorithms that those people have invented to understand and study free energies in solids, very complicated solids, crystals, liquid crystal phases. It's free energy measurements for solids. And the Frankel lab tool is really like becoming one of these fancy algorithms. It can be adapted to measure things in glasses, and this is the work that we've done. It was not easy, but very fun to do. And the third thing that we've developed tools for is the Franz-Parisi potential. Okay, if I remember in one sentence what it was the free energy cost to have a fluctuations of the overlap between pairs of configuration. And it's a free energy measurement, just as the Frankel method is a free energy measurement. And just as these guys involve thermodynamic integrations to get to the entropy via the free energy, actually. So in all of these cases, we do some kind of thermodynamic measurements. Some are easier, some are more complicated. This one is the most demanding one, but that's the one that's closest to the mean field approach. Again, to learn how to do this, I opened that book that I didn't put in the trash, and it's all there. The method have been developed to study phase transitions for complex liquids, say, complex fluids of matter systems. It can be adjusted to study the Franz-Parisi potential. Once you have this guy, you look at the free energy difference between the large Q and the low Q, and you define your configurational entropy this way. And all of this has occupied us quite a bit in the last few years. And most of it, again, has been summarized in that article, I believe. Most of it, not everything. So that's 3 different types of measurements of the configurational entropy that we have. In addition, this one is good because you can directly test whether the shapes and everything, the features of the Franz-Parisi potential can be seen in finite dimensional systems. So I like this one much better because it's the key quantity that you would like to measure if you want to explore the physics associated to the random first order transition system. So let me show you or sketch how this is looking like when you do your computer simulation and you work hard and you learn how to do this, you reconstruct your free energy, You get a V of Q that at high T is looking boring. So boring is easy to find usually. And then you go to your lower temperatures and you detect something that you've seen before in, again, phase transition. You see something like this, then it's fairly straight like this, and then it goes like this. Again, I'm in the blackboard and I'm drawing, so I make it very, very nice. In practice, it's not as nice as this. But it has the following interpretation. I'm going very fast because lunch is waiting for us. So remember what we had in mean field. We had this prediction that we are approaching a first order transition. You know that this cannot happen in finite dimensions. If I go at intermediate values here, and now I'm using real space. If I ask that my order parameter is halfway between one phase and the other near first order transition, the system decides to phase separate again, and it's lowering this energy. So that construction where you take the two minima and you connect them is essentially creating an interface, and this is the signature of a phase coexistence. Again, you go back to these books in my office over there, you go back to first order phase transition, it's all there. Okay? Maybe to finish, when we were looking at the gas, liquid, it means I'm going there and the system is phase separating between the liquid and the gas. That's the exact analog in this language. So out of this, we can get many things. We get that guy, which is the free energy difference, which is the configurational entropy. Okay. But in addition to measuring the configurational entropy, of course, I have this underlying phase transition. I can see it, I can probe it, I can tilt the potential, I can induce the first order transition, I can see everything. And the bottom line, because we are getting to the end, is if you combine all you've seen in your computer simulations for the Franz-Parisi potential and the configurational entropy, everything that I've told you from the mean field theory, it can be seen in the three-dimensional, it can be seen in the three-dimensional atomistic models, okay? So the decrease of the configurational entropy, the emergence of this tail in this Franz-Parisi potential, the fact that that thing is going down, the fact that when I tilt the potential, I'm inducing a phase transition, everything is there in the thermodynamics of those supercooled liquids. So I'll leave you perhaps with these phase diagrams to get finished. Okay, so the phase diagrams that you find are like this. And I'll just repeat again the mean field theory, but as viewed from the computer simulations. So I go back to my extended phase diagram with this field epsilon that was conjugate to my overlap. So remember what we said before. We said, or somewhere there could be a TD, there could be a TK. That's the mean field constructs. We said if I call the system in a supercooled liquid in finite dimensions, this one cannot be seen, but maybe this one can survive. I didn't give any argument against it. So now we can do two things. We can do at epsilon equals to 0, we can measure the configurational entropy. And this is what I was explaining to you before. And so if we do this in a supercooled liquid, so we measure the configurational entropy at epsilon equals to 0. Somewhere there would be those TD and TK things. And so typically what we find, I'm trying to make it a bit not too convincing, but a little bit convincing. Okay. So typically we find curves that look like this. Okay. So we measure as best as we can by like zillions of methods and models how the configurational entropy decreases. So earlier simulations, the Srikant simulation from back in the day, they stop here. We extend down to extremely low temperatures thanks to the swap. Essentially, it goes down very quickly. And if we play the Kautzmann game, okay. If we play the Kautzmann game and extrapolate our data, we would locate some Kautzmann transition somewhere. So we are not yet at 0 close to Kautzmann, but we jumped considerably thanks to the swap Monte Carlo algorithm. So that thing, then we can locate and we put it back on that diagram. So we follow the configurational entropy and we get the feeling that it's going to fall there. The other thing we can do is we can play with the Franz-Parisi potential and these phase transitions that I was mentioning before. And I've told you and I've tried to argue, provided you're just above and you tilt and you induce that thing, you may or you may not see a phase transition, and we see it very convincingly in computer simulations. So this is where the swap simulation can go, This is where we stop. So here we can work in equilibrium. We can test this idea of phase transitions. And what do we see? We see a line of first order transition very convincingly. So that one, we have done extensive work on this. So, the first order transition, it's very convincing, the evidence for this. And we go increase the epsilon, and the system jumps through a first order phase transition towards a large Q thing, which is the analog of what I've drawn over there. Then we follow this first order phase transition up to a point where relatively convincingly we see a critical point as well. So the critical point here, we can see critical exponents. We've tried the best we could. We could not, say, measure them from scratch. So the only thing we've did is we've checked that if we take the known values for the random field Ising model and we look at the details of the fluctuations over there, everything is compatible with the random field Ising model, even though we don't have a large precision on the exponents. And over there, what we see is just a crossover for the phase transition. So that's what we can do now with simulations. Because of the swap, we can go to very low. We can study everything, the configurational entropy, this first order line, the second order critical point. And this, I think, is not disputed by anyone. This is things that we see. The only thing that's disputed is the Kautzmann idea of those things and those things all converging to a Kautzmann point. This corner here is where we cannot yet approach. We don't have tools to approach. The machine learning tools, if they work one day, they will get us there. Okay, we will be able to approach arbitrary colors to TK, cross this, and measure all the properties of TK. That's the dream for the future. But this is what has been quite convincingly, I would say, seen in computer simulations in 3 dimensions. We've done it in 2 dimensions, and we see very interesting phenomena that I don't have time to explain. 4 dimensions, 5 dimensions, infinite dimensions. We haven't done such a lot of work there to see whether it smoothly goes to the mean field limit or not. We don't know that thing. And that, I think, is where I need to stop. So I wanted to say a little bit about the dynamics, but that's fine. But at least I'm closing again by going over the mean field theory as applied to computer simulations a little bit to close. 3 minutes late. Thank you. Questions? I will be there this afternoon in the tutorial, so if you want to ask more questions, I'll be there again at the end of this afternoon. And we can go for lunch, or we can take 1 or 2 or 3 quick questions. Your choice.
What is the response function that diverges at this critical point?
Response. Then that's simple. It's how fast the overlap is changing when you apply a little bit more of an epsilon. So if you're here, if you change a little bit the value of epsilon, it means your order parameter is highly sensitive to the change of your external field. Just as again, my Landau sketch where you get very flat and then you develop the 2 minima. At the critical point is where the free energy is super flat and you have these large excursions. So fluctuations are big, but susceptibilities are large. So response functions are diverging. So that's exactly what we measured there. Sorry, that's not exactly what we measured there. Instead of measuring the response function, we measured correlation functions, but via fluctuation dissipation theorem, it's equivalent. So what we've characterized in great detail here is precisely spontaneous fluctuations of the order parameter, so the Q. We've looked at histograms of the fluctuations. They get very broad at the critical point, bimodal below, and at criticality super broad with the weights that is diverging with the system size with some characteristic exponents, So that's the analysis we did. Again, it's textbook analysis to this complex problem, but it's Landau types of things.
Okay, so he's going to be there for a tutorial, but that is the end of his lectures, and let's thank him for a fantastic set of lectures.
Well, I wanted to say thank you to the organizer. I wanted to say it at the beginning, so it's very nice. So I wanted to say thank you for giving me the opportunity to be there and for the invitation. Thank you, friends, for coming and visiting. And thank you for all the questions. I mean, it's been, I think I've given lectures on these topics before. I never had such an amount of questions. So you're very dynamical, and that's great, I think, because it's helping us when we teach to just understand where you are when you're totally lost, or when you can interact with us. And I can see when I talk to you during the questions whether you get it or not. Sometimes I say, and I say, okay, I explain well. Sometimes I see that. So I slow down. So all the questions I think were great. Thank you very much.
Let's be done.
Still time, no? There is still time. Yeah, 3-4 minutes.
So this is the last class, so we still have tutorial. So questions there. So maybe you can just write your photographs still there. Just write down your names and then
Okay. Okay. Okay, can you hear me from the back? Yeah, all good then. Okay, so welcome to the last lecture, okay, for the entire school, as Sanjay mentioned. So I'll try to keep it short, let's hopefully, yeah, and also like less stressful as possible. Okay, so what we did, let's have a brief recap. So, there are two phases of sort of like the development of the field of resetting. Like in the initial phases, we were very much interested in understanding different type of first passage properties and spatial properties when we had instantaneous resetting. And of course, after that, slightly, attention changed because of people started doing experiments and things like that. And also, we were more focused on understanding different type of applications. And when this, the focus changed, we also understood that doing resetting in 0 time, or this teleportation, so-called teleportation, is actually this is a major hindrance for any kind of practical realization, right? So because taking anything from one place to another place, even if you do it very fast, there should be a time involved. Okay, so that is that that was sort of the onset of this new kind of thought that we should probably consider about finite time resetting. Okay, that's my mobile. Just 1 second. Okay, my apologies. Okay, so so initially what we developed in the first few classes, like we calculated spatial properties, mean first passage time under different type of resetting mechanism, etc., right? And then at the last phase of the class yesterday, what we developed. So if you think about a general search process and also consider the fact that the resetting process is actually a finite time process and can be conducted in various different modes, how this mean first passage time should look like. And then we also understood that then we need to go beyond these typical backward renewal equations, what we do, and more towards an approach which is more of an abstract approach, but it's also a very powerful approach. This is what I called a black box approach, right? Last day. Okay, so let us just have a brief recap of what we did. So we started with this finite time resetting. And the motivation was that, okay, if you have any kind of search process happening somewhere, and then you have multiple targets, and just assume that there is a home somewhere, okay, and then you have some sort of a dynamics taking place. So you have something like this, and at some point of time you feel like that you have to reset, right? So if you want to reset, so usually what we were doing before, we were just taking the particle from here and putting it back here, right? So, and what we learned that, okay, this is probably not a very good thing to do when it comes from the practical purpose. So now it should take some finite time, okay? So when we think about this finite time, it also should depend on where from the particle is going, is being returned, right? And this also, and then this, the process can repeat, etc., etc. And let's say like this. So you could have some sort of a topographical constraints. So let's say that the particle cannot actually go via this. So you could take a different route. So you probably have to continue, like from this point, you want to reset, let's say, but you cannot go via this. So maybe you have to go something like this. So it doesn't matter like what kind of path you choose. So you have quite some arbitrariness in this return path. So x2. And the only thing what we assumed that during the return phase, this is the return, or like after the resetting, the phase which comes, the particle is blind, in the sense the particle cannot see the target. So the particle can see the target only during the original search process. After the resetting phase starts, or the return phase starts, when it comes back via some very arbitrary general way, but it cannot see the target, okay? So this is the reason we call the target is blind while coming back, okay? So this is an assumption we made when we derived the formula yesterday, okay? So let us just recap the formula we had, right? So again, we had two phases, right? We had search phase, which is basically the original dynamics, and then we had the return phase, okay? And we derived this formula, that the mean time that eventually the particle or the agent, whatever, it finds the target, any of the targets. Okay. So this definition of how you, like what is the time? So this time either to find all the targets or one target or two targets. This is up to you. In this particular case, we have assumed that as soon as the agent finds one of the targets, I stop the process. Okay. This is what we assumed. Okay. So let me just recap the formula here. So we derived. So TR was okay, so if you recall, right, so this was the term for the original instantaneous resetting process, right? So I will just write it instantaneous return process, okay, because it was taking 0 time. So this is the contribution from which we knew from previous calculation. And you see that there is a positive contribution now which is being added because of the return, right? Of course, because return will take time. So there is a positive contribution. So this is the instantaneous return search process, and this is essentially coming, the contributions are coming because of the finite time return process. Okay? And as I have emphasized again yesterday, and let me emphasize it again, that it depends now the modes of return. So let me just maybe stress on this following point. So this formula, as we can see, it holds for general resetting distribution, resetting time distribution. Also, as you can see that I have not made any assumption on the underlying process. So the underlying process essentially means that it holds for arbitrary first passage time process. Some sort of, you have quite some arbitrariness in the dynamics itself, the underlying dynamics. Then this formula also, as you can see, that it doesn't really depend on the particular form of tau of x. Okay, so the various modes of return are that also is available. Okay. Well, there are one or two more points which I also would like to emphasize. So as I mentioned, this tau of x, if you think about tau of x, so let's maybe just imagine just a one-dimensional setup for this. So you had some sort of a stochastic trajectory, and from there it returns, right? So as we can see, this is your tau of x, return to the initial condition or resetting condition, whatever way you would like to call it. Now, this is the position, right, which is random. Okay, so this is the only random component in tau of x, right? Okay, so but the form of tau of x is usually given because you have given the form of how it returns, right? So that will be given usually. But this is all. There is also a possibility that this tau of x itself could be random, right? This is also like very fair assumption. So I will try to come to this kind of setup a bit later. Okay, but for the time being, you can immediately understand that if you have this tau of x, if it is a random quantity instead of having a deterministic function, okay, where x, in this particular case, I also have to average over this random time, okay, this random return time, okay. So the formula does, like it will be easily modified. So instead of having this tau of x, you just take the average of tau of x, right? Okay, because the stochasticity in this tau of x then comes from the way the particle returns to the origin or the initial condition. Okay, so this is what it is. So this is a bit of generalization which you can do, but you will see that these two give completely two different type of experimental setup. Okay, we will come back to this later on. Okay, so if you have, do you have any questions here from yesterday? If not, then we'll just go on then. Okay, so like as always, like we would like to simplify our life, and then first thing you can do is that you can take the resetting time coming from an exponential distribution. So let's say that if I take something like this, so the resetting, let's say, is taking place with a certain rate r, right? And every time the reset occurs, then the particle comes back with very general tau of x. So then you have already calculated all these quantities, right? We have done this before. This guy, this individual, all these things. And let's plug in everything together. So we will get TR equal to 1 minus R. I hope you remember what is this guy. What was this? Laplace transform of the underlying first passage process, right? Yeah, so let's just do a small algebra over here. So this is tau of x, and then we have, yeah, okay, forgot to. Let's write this, right? So we have dt FRT, right? So I have dt r e to the power minus RT. Then we have dx tau of x, right? So you see that this, I can take it inside, right? Because none of this depends on time, right? So I take this inside. I have this one is t tilde r, right? This is something which we have calculated already before. So let's take this here. So 1 minus r. Okay. So if you do that, so then if you take this inside, then it becomes the Laplace transform, right? It becomes the Laplace transform of the propagator. So we can just simply write this formula effectively in this way. So d of x, tau of x, G0 tilde x is equal to r, s meaning the Laplace parameter, right? And then you have this. Okay. Okay, the reason I chose this exponential resetting because the exponential resetting time, because I want to demonstrate a few things for different return times. Okay, what can happen? Yeah. Maybe I have done that, yeah, maybe, yeah. But this G0, okay, yeah. So, yeah, maybe I have made that change in the notation. Yes, I was using P, I suppose, right? And I was using P and PR, right? Yeah, okay. So one crucial change is not only in the notation, but also conceptually, if you think about it. So this G0 is also in the presence of the boundary, right? So this P, PR, which we wrote, I mean, I think I wrote both for the, even for with the absorbing boundary, I wrote P and PR. In this case, just, I mean, notation-wise, yes, of course, I have changed. But let me just do the following, maybe, for the sake of consistency. This is fine? Yeah? Okay, I think all of you guys are happy now. But what is crucial, I want to add here, that this is in the presence of absorbing boundary. Right? This is something which I stressed, right? I mean, this in the sense that this is not normalized, right? Yes. Okay, so we have done this. So now what I would like to do is I would like to spend some time on these possible experimental setups which people have done in the last two or 3 years, and would like to, derive a few formulas or relations, and the behavior of the mean time with respect to certain parameters, okay, and how we can use this particular, this particular formula we have derived. Because you see, this formula we derived in the context of generic search processes, etc., right? This was typically the idea, what we wanted to do here, right? But while doing that, we also realized that this is also a very useful, formalism when it comes to dealing with experiments, right? Because it's also in the experiment you have these finite returns, right? So let us spend some time on these experimental setups, okay? Okay, let that formula be there. Okay. Yeah, so a typical experiment, you know, like, is there anyone here who actually works on experiments or something like that? Probably not. Okay, so maybe I need to give some introduction to this. Very simple setup, right? So when we think about, you know, like playing around with particle in a harmonic trap and things like that, right? So this is actually a kind of setup. It's a very classical setup and can be done in a very simple way, okay? So what you need to do essentially is that you have to create an optical this harmonic trap using some laser, okay? So this is something which is for which what is it? What is his name? I forgot who got the Nobel Prize for this. Ashkin. Okay, so he got the Nobel Prize for this, right? So how to actually trap a particle, okay? And then of course you can generalize this concept for many other more complex systems. Okay, but whenever you see here or you know hear different kind of stories about a particle being trapped by some potential, etc., this is what is going on. Okay, so we will also consider a similar kind of setup. So let's imagine that you have, you know, like you have a two-dimensional plate, okay, where you have put some water which will serve as a background medium. Okay, so this is like water. And then you have put some silica particles. So silica particles usually is micron size. Okay, so these are like polystyrene beads or could be silica particles or something like that. Let's just, there are many of them, but let's just assume that there is one, which you are like looking at. So and let's just consider this is my home, right? This is the center origin of your of this plate. And then what is happening is that you want to do this resetting experiment. Okay, how do you want to do that? Okay, so first thing you do is that I have chosen this if t, right? So the resetting time I have chosen from exponential clock. So what I can do is I can just first create an array, different times, right? I don't need to do the experiment for this one. This is just it takes for MATLAB like 0.3 second to generate this number, right? Once you give R. But I have these numbers with me, okay? So now at t is equal to 0, I start from here. I have the particle somewhere here. Let us call this as an origin, just for the reference frame, okay? And this silica particle diffuses, right? So it diffuses, right? And then I pick this number from here, okay? And I see that, okay, this R1 is 1.2 second, okay? At this point of time, let's say it's here, the particle is somewhere here, it has diffused till here, okay? So now I want to take the particle, I want to reset the process, right? So in simple words, I want to take the particle to its home. What I'm going to do, so there are many ways to do this, but let me just give example of one particular type of experiment. What we do is that we project an optical trap on this particle, okay? In the sense that the optical trap usually is, like defined in this. So this is basically two laser beams coming together, and there is a radiation field because of which there is a potential minimum, okay? And this potential minimum is not like a potential in the real system where it goes to infinity. It has a certain, like distance up to which the particle can feel the potential, and after that it is shallow, okay? But so anyway, those are like experimental details, but never mind. So you project the trap there, okay? And then what you do is you keep the particle inside and drag this trap from here to here, okay? So this is same as what we have done for the case of general home run search process, right? So it will depend on from where you came. So this is my X. And for the time being, just generically assume that, okay, it has been brought by some particular mechanism, okay? So this is a process which will keep on happening, right? So you again, the particle will diffuse, and you again, where you pick up this number, the next number, right? And then you again hold the particle here, and then bring it from here to here, okay? And now, of course, you can ask the following questions: so what are the ways I can bring, right? What are the modes of return? Okay, so we'll study 2 or 3 different type of modes. So first is the simplest one probably. You just assume that, okay, like it doesn't matter. I will always take this particle from here, okay, trap it and bring it from here to here with a constant velocity. Okay, so return with a constant velocity. Okay, or then somebody can tell me, no, I don't want to return with a constant velocity. I want to always return with a constant time. Okay, so it doesn't matter. In some cases the trap has to operate faster. Some cases maybe like accelerate, deaccelerate, like whatever, depending on what. But you want to keep this tau of x fixed. Okay, so this is in fixed time. So tau of x is tau naught. So it will not depend on x, right? This is rather a very simple setup, right? You can also have an accelerated process, right? You can think about that. Okay, I am bringing it with under an harmonic force. Right? So in that case, the return process is just something like this. So return process would be, forget about m, x dot double dot is equal to minus u prime x. Okay, while u of x is what? U of x for harmonic spring, right? So I said for this, u of x is half kx square. Okay, and then of course there could be also other type of ways. Like for example, you can bring the particle with spatial dependent velocity and things like that. Okay, so like these are the realistic ways you can bring the particle using a laser trap. Okay, from one place to another place. And of course, for individually, all of these cases will give rise to different mean first passage time. Okay, so if we do the first case, so you see that if you want to calculate it, so first thing is note what is tau of x. What is tau of x in this case? Okay, I am not going to answer this. Okay, so what is tau of x? What is tau of x in this case, right? So let me just simplify the problem. So you have this one-dimensional trajectory, let's say. This is your x, and from here it comes back here with a velocity v, r, right? What is the time it takes? There are no fluctuations. It just is coming in a straight line. What is it? Mod x by vr. So what you do, you have this expression for the mean, you just plug in there, right? That's all you do. And now, of course, we have a silica particle which mimics a real diffusive system, etc. I can use the properties of the diffusion, and effectively what I get is the following. So we have 1 by r plus, let me just write this now. So let's just call this I'm just looking into the projection of this system in 1D. Okay, so I have this, but you can use it in 2D very simply. So you have this x, from there it comes back, keeps on doing this process till it reaches here, right? This is at L, this is 0. Okay, this is VR. So L by VR, and then you have a finite quantity. Okay, it's just bookkeeping calculation. You don't need to worry about it too much. Yeah, but the point is, this is if you calculate this using the formalism which I gave, and then you try to do an experiment with this simple silica particle, and you can see that they fit to each other. Well, of course, one can argue many different things, that you are actually mimicking a computer, like programming itself using a system which behaves like a diffusive system. But nevertheless, it's always nice to see that like you have some proof of principles which you can actually check through experiments. Okay. And if now if I, let's say if I want to plot this guy, right? Okay. So r is equal to 0, what is happening? So now when I don't have resetting, then what happens, right? For this case, let's say. This is something we have studied, right? So it goes to infinity. It's a diffusing particle, right? So it goes to infinity, and then it has the same behavior, okay? So it will have the same behavior, okay? But the only thing is, now you see that because you have this additional time, right? Now there is a delay time because of the finite return. So whatever your instantaneous process was, so we had this instantaneous return process. So now this time will be somewhere up, correct? Okay, and you can go from here to here by changing velocity, right? Because you see that if you increase your velocity, as if like you are reaching almost in the instantaneous limit, right? If your Vr is equal to infinity, you hit the instantaneous process, correct? Okay, so this is what I have shown. So this is Vr increasing. Okay, so this is what you can show, and then there, of course, there are different optimalities which arise here, etc. And it goes in this way, so one can actually analyze this kind of optimal resetting rate, etc. here. Okay, so let us do maybe another simple setup. Okay, so let's do the fixed time one. Fixed time one is actually the most trivial one, because you see, which part I should remove? Maybe I will just remove this part. I want this schematic to be here. So we have this. So if you do the fixed time case, right? So you see that in the fixed time case, the case 2, right, we have tau of x, which is actually independent of x, right? So it's just like nothing, it's almost like the same as instantaneous resetting process. Of course, it's not impractical, but it just takes finite time, okay? But always same time, doesn't matter where the particle has gone, okay? So you have to you have to work hard with your optical trap to achieve something like that without any fluctuation. But the maths becomes essentially much simpler, because you had this d of x, tau of x, right? And then we had this p, something like that, right? But then it doesn't matter, right? This one, it just comes out, right? Because tau of x is now tau naught, so it comes out. So then, the d of x is there, p tilde x are there, right? So now you can complete the integration, okay? So it rather becomes very simple. I will just give you the answer here. So I have this T of R, right? If you just take a look at your note, so we had this term, right? Initial terms. And now, but when you add this finite time, like finite time resetting, constant time resetting, return process, so it just gives rise to this tau naught, but the other terms remain the same, okay? This is something you can check later on. Okay, this is simple. Okay, this is not very, like it's not rocket science, just very simple. Okay. I'm doing all these exercises because these are straightforward exercises, but it's also good to learn these exercises, because you can manipulate your system to get all these kind of different forms and shapes of mean first passage time, depending on who is doing experiment, wherever, like on what kind of setup they have in their disposal. So let's now do the third case, where I said that, okay, as if like there is a harmonic trap, right? So which is being pulled. So you have mx double dot is equal to minus kx, let's say. Okay, let's just take this, absorb this mass in the dimension. Okay, so if you do this, there is no noise, right? So it just comes back, okay, under the harmonic force, right? If you do this, what you get is the following. So let's do this simple exercise. So I have the solution of this is x of t x0 cos square root of k times t. Okay, this is just the solution of this one. Okay, and from here, what you can calculate? You can calculate the t, right? So what is it actually? So it essentially tells that you are coming under the harmonic force, right? So you're starting from x0, and you are looking at the position at at time t, right? So x at time t, and this is my x at time 0. This is what I noted as x0, right? And I am interested in the time it takes for the particle to come from here to here, right? So I have the solution for x of t. I can just rewrite it on the other side, right? So if I do that, what I get is something like this, right? So t is equal to 1 by square root of k cos inverse x by x naught. Okay? So now let me just draw the rest part of this, right? So what will be the rest part of it, right? So this is my, like the resetting trajectory, right? And this is the position from where it started returning, right? But this time it is returning under this harmonic force, correct? So this is my x, right, from where it has started, right? This is at arbitrary position, and this is random because it depends on whatever the time you have from coming from the distribution of resetting waiting time distribution. And then this is basically, it's returning to 0, right? Okay, so how should I rewrite this tau of x here? So tau of x should be, tell me what it should be. What is x here? And what is x naught? What is x naught? What is x? Where are you reaching finally? X is equal to 0, right? Yeah, so cos inverse 0. So cos inverse 0 is, yeah, right? Okay, so as you can see that in the case of harmonic force, right, it is actually independent of x naught. So it actually doesn't matter from where it is coming, right? It so happens. So it doesn't matter, like it is coming from here or somewhere here. It's independent of x. Okay? So what you can do, you can now plug this guy inside the formula, right? So if I do that, what we get is something like this. So you have the initial term 1 by r, which is appearing everywhere, right? Because this is unaffected, right? This is the instantaneous case. Plus you have this new term, which is given by pi square root of k. It's very simple because again, this tau of x is becoming like this guy, right? It becomes independent of x. So you can complete the integration. So of course, now if you make the plot, so tau r versus r, t of r versus r, so if you do that, so how it should look like? So what is the instantaneous case in this problem? How can I reach the instantaneous return limit from here? Sorry? K tends to infinity, right? So that should be, for sure, that should be the bottommost plot, right? And then of course, as you are making it finite and finite, so it will go up, right? So it will be something like this. Okay, so this is my k is equal to infinity, and then it becomes lesser. Okay, and the mean time keeps on increasing. Okay, so I think I have been able to convince you, like there could be different modes of return, etc. Okay, and using, depending on who is using what kind of experimental setup, you will get different results. Okay. Okay, and then, but at the end of, also like 15 minutes back, what I said, that you also could have a situation where this return time also could be random, right? And I say that I will try to explain what could be this situation, okay? So let me also try to give that situation. So you have this one first, right? And I give this one. So we'll also get back to this experimental setup again, but let me just keep it for the sake of comparison. So you see that in this case, what we did, right, is basically every time you had a resetting, you project the trap on the particle, right? So instead of doing that, what you could have done, or like depends on who is doing the experiment, in which group, etc. So let's say that you are going somewhere here, right? Now instead of actually projecting the trap on the particle, what you could have done, you could have switched on a trap here. Always at the origin, Okay. And now because the trap is at the minimum, right, at the origin, so what the particle essentially feels like a force towards it, right, towards this minimum, correct? So if I look into the trajectory of the particle, right, so this is my trajectory, let's say, and I'm just focusing only during the return phase, right? So this is the, let's say this is my origin, so this is 0. So it started from somewhere here, right? This is the random position it had, right? Some x1, let's say. So it will essentially keep on going down, right? Because it wants to reach to the potential minimum, right? So instead of, like every time creating a setup where you have to actually project the trap on the particle and bring it back all together, keeping in mind that the particle cannot escape from the trap, instead of doing that, what you can do is that instead of projecting the trap on the particle, you just switch on the trap here. Okay? So in other words, this trap essentially is like stochastically switching on and off. Okay? Of course, now if somebody is doing an experiment, there is always the possibility that you switch on the trap, the particle is quite far. So even if it's, as I said, it's not an infinite potential, right? Like in theory. In experiment, it has some sort of a width. After that, it becomes shallow. So there is, of course, if somebody is doing the experiment, also they have to be very careful that the particle is within the strength of this trap, right? So this is, if somebody wants to do this calculation, so nothing changes at all, okay? What you need basically this tau of x, right? But now this tau of x is also averaged. Averaged over what? Averaged over this stochastic trajectory, the return trajectory, because the return is also now stochastic, right? But you see that for harmonic potential in particular, this is rather a very simple problem. Why? So in harmonic potential, what is happening, right? You know what is a Langevin equation, I suppose. So it's like a particle in a harmonic potential. So it's like dx dt is equal to minus k of x plus there is a noise, right? And the particle is starting from somewhere here. So the initial condition of this guy is x1, which is random, of course, after each interval, right? After each resetting event. But then every time it has to come back finally at the origin. And what is this t? This t is essentially this tau, which is random quantity. So you have to essentially solve something like this. You are looking at the particle which started at x1 and just waiting when the particle reaches to the origin for the first time. As soon as the particle reaches to the origin for the first time, okay, you stop the process. So essentially it means the particle has reached here, okay. So again the particle goes back to the diffusive phase, right? It keeps on searching. Yeah. You are very close to the boundary, yeah. Yeah. You could also still get absorbed there, in principle, yes. That is something which we have not done here, because you see that when we say that we return, right, we say that the particle is actually blind. So it cannot see the boundary. But that is what goes into the formalism. But you can try to extend also that formalism, as you are saying that you could have once in a while a large fluctuation, so it can just go to the other side, right? It can always go uphill once in a while. And then it can actually hit the target during the return phase. But then this formalism which we have done so far, there we have explicitly assumed that the particle during the return phase is actually blind. So it cannot detect the target. Okay, so of course then one has to generalize this problem. Okay, so I hope this part is clear, right? Like, so before this problem we have discussed only the deterministic return, so to speak. But this is something which we call stochastic return, and it actually has a purely different, like experimental origin. Okay? Okay, so now what I would like to do, I would like to now, like discuss this experiment for another 5 or 10 minutes, and then we will be done with the experiments. Okay, so like in an experiment, right? So we understand this experimental mechanism, etc., right? But let's say somebody is doing the experiment. So this lab actually has to invest on energy, so to speak, right? Because you have to keep a laser on for some time, right? Because you are dragging the particle, dragging the particle from here to here and making sure that it is inside, right? So there is a power which you have to give by the laser, right? And that there is an energy. There is the energy cost for that, right? So usually, like from radiation theory, usually like from the theory of these optical traps, etc., you can write this energy, okay, in terms of the return time, okay? So it's not a very complicated formula, right? It's a very simple formula. What does it tell you? So this is the power, okay? So this power meaning that the laser, when you switch on a laser light, there is a power you have to give, right, to keep the laser on. So this is that power, and usually this is a given number, okay? Let's say in this kind of experimental setup, at least the experiment I know, this was fixed at 1 watt, okay? So this is a number for the time being, you can forget about it, okay? But then this energy, it depends on the return time. And as you can see, because this return time is stochastic via x, so this guy also will be stochastic, right? So you can try to calculate this mean energy invested when you are doing this experiment, okay? Well, of course, theoretically, when we do this kind of calculation, we don't really care about, these details, right? But if you're doing an experiment, you actually have to keep in mind that you have all these additional constraints. You cannot do things, without within indefinite budget, right? So you have to always keep in mind that, okay, there are certain things, there are certain, like I have some sort of constraints within which I have to do things, right? Okay, so what we need to do, right? Let's say if I want to calculate this guy, so this average over this is essentially the average over this, right? Okay, so this is actually very simple. So let us go back to the formula, right? So again, let's take this experimental setup again here, right? And let me just draw one trajectory. So I was like here, and let's say I am here, okay, somewhere here, okay. Now from here to here, I have to go back, okay. So I go back from here to here with a constant velocity r, vr, and let's say this is the distance from where I was going back. Okay, this is a 2D. Okay, so RD is square root of x square plus y square. Okay. Now I want to calculate the time it takes for me to go from here to here. Okay, statistically, right? Because each case tau of x will be something else. So I want to do an average over that, right? So what will be the distribution of tau? So let us try to write the distribution of the tau. So the distribution of tau should look something like this, okay? So let me first write it, and then we will discuss about it. Okay, so first of all, the particle can reach here, right? And what is this? What is the time when the particle is here? Is drawn from resetting distribution, right? So now I think you should be able to understand this. So let's say I have drawn this resetting time first, right? And at this resetting time, the particle is basically here, right? So all this information should go in, right? How the particle has actually reached here? Via the propagator, right? And what was the propagator? P, let's write it in this way, P R D T, okay? This is one, first set. But now this, like you can reach at RD, right? There are going to be many different RD, right? But not all of them will give rise to this T, right? So now what you have to do, you have to only take those R, okay, which will give rise to T, right? So then you have to average over all this, all the possible RT, okay? Okay. Okay, let me know if you are lost. Okay. This is the domain of your interest. Okay. you see that this is I am trying to calculate the waiting time, not the waiting time, the distribution of tau of x, right? So tau of x, right? And what is tau of x here is basically tau of Rd, right? And I have fixed tau of Rd to be t because I am trying to calculate the distribution with a running variable, right? Which is basic for a given value t. This is the way you can write it. Physically try to understand. If you don't understand this formula all the way, that is also okay. But at least physically try to understand what is happening. You need to average over the following quantities. First, resetting time, right? Which goes on here. And exactly at that resetting time where you were at Rd, right? But then you could be anywhere in the space, right? Because you will have different realizations, right? So you have to integrate over these Rds. That is all I have done. Okay? Keeping this constraint that t has to be tau Rd. Okay? Now check that this phi of t is actually a normalized distribution, and then I think you will be happy. Okay? Check this. Okay? You can do it during the tutorial break. Okay? Because it's a normalized distribution, right? It's a waiting time, so it also has to be normalized. So you can calculate this. Okay? Check that this is true. I don't want to get into too much details, so let's say that I want to calculate now this t average, right? T average essentially is basically tau of x average. So what should I do? I will do basically an average over this guy, right? So I will write 0 to infinity t phi of t dt. Okay? Okay. Which is the part I can remove. Now there is an extra piece of information before I calculate this, right? I need an extra bit of information, which is basically that I went with constant velocity, right? So this tau of Rd is just, it is going radially, right? So Rd by Vr. Clear? It's very simple. So you can actually do this calculation. And once you do this calculation, you will get the following. So phi of t, you see that you will put this tau Rd over here. So it becomes t minus Rd by Vr, right? And then there is a delta function. So first you can do the integration over Rd. Correct? And then of course then there is these other things which you can do. Okay? So effectively what you get is something like this. If you do this calculation, I am not getting into too much details of this. So this alpha naught square, Vr square, t, and then you get a Bessel function. Okay? And once you have this, you can immediately calculate the phi of E, right? Phi of E being, I think you have forgot what is E now. This is the E, okay? And we were interested in the average energy, right? So this average energy is given by something like this. Okay? Okay. So let me know if you have followed the steps, okay, if not the maths. Okay, this is something I want to know. Okay, just don't be lost. Okay, so what I have done is the following, right? I have tried to calculate the average energy I need, right, on an average for this laser to operate. Okay, it's of practical importance. Okay, let's put it in that way. And we saw that this energy is proportional to the return time, right? So if I want to calculate the average energy, I need the average return time, right? The mean return time. Okay, and in this particular case, I was returning with a constant velocity Vr. So let's just write Vr, right? So this tau of Rd is Rd by Vr, right? Similar as 1D we had mod x by Vr, right? Now this Rd could be anywhere, so I have done an averaging over Rd. And what is the other random variable? Just the resetting waiting time. That also I have averaged over. That's it. Okay. Never mind the details of the calculation that you can that you can do it also like using a simple 1 or 2 steps in Mathematica. Okay. So what is the take-home message? The take-home message here is that E is actually proportional to 1 by VR. Okay. This is a trade-off relation. This is an energy trade-off relation, right? Why do I call it a trade-off relation? Why do you think so? Absolutely, right? So it seems that the mean energy actually is inversely proportional to the velocity, right? And now if you think about it, it makes sense. So the faster I return, so of course the time it takes will be lesser and lesser, right? Right? So it's basically I'm going back to the instantaneous limit. So we are going to infinity was the instantaneous limit, right? So this is the reason, this is a practical point of view, this is the energy trade-off relation. Okay? Now the question is, can I actually do that? Because think about it, that when we did the instantaneous teleportation, we didn't invoke any mechanism, right? We just say the particle is here, next moment the particle is here. And now I'm trying to, invest a laser trap. Who will do this work for me? And now this laser trap is here, right? And I somehow have managed to hold the particle inside this trap, right? And now my plan is basically to go from here to here with a very high velocity, right? If I try to do that, the natural consequence will be the particle will escape from the trap. Okay? So if I try to go from here to here, right? With a very high velocity, right, I won't be able to keep the particle inside the trap. It will just escape. Okay? So because, this trap is, as I said, this is a practical trap. This is not really a, a hypothetical trap which has which goes to infinity. Like for example, typically when you think about harmonic potential, you think something like that, right, which goes to plus minus infinity. Right? This is what you do. But what should a trap look like? Right? So this should have something like this. So it is harmonic only at the center. And soon after, it becomes shallow. Okay? And now if you just think about it, right? You have this guy, right, effectively, which is basically this one, and now you are trying to move it very fast. Will you be able to keep the particle inside the trap when you are moving actually very high velocity? You won't be. Okay? So it will escape. So from practical point of view, you actually have a cutoff on the velocity. Okay? And this cutoff at the velocity actually can be found from the people who actually have worked on different type of, different type of traps using different type of spring constant in the sense like the stiffness, etc. and all. And so also depends on the viscosity of the medium, etc. Depending on that, you can show. This comes purely from the the theory of optical traps, etc. So there is a maximum velocity which you can gain, okay, which is given by this. Okay, let me explain what is it. Okay, so this C is just a number. Okay, so you don't need to worry about it. And what is this P? So P is basically the power. Right? Now you see that everything is important. Given a power, immediately there is a velocity which will be decided, right? You increase your power, maybe then you will have like a higher velocity. Okay? For a given power, you only can go up to this velocity. Okay? After which there is no guarantee that the particle will be inside the trap. Okay? So if you have something like this, right? So I can actually try to calculate the minimum energy, right? Because that is what we are after. Because we are trying to, minimize our energy, right? This is what we are trying to do. With investing more and more velocity, we are trying to reduce the energy, right? So we are now interested in the minimum velocity. So if I put this Vmax, right, some constant number, right? So let me just try to see what is it. So I have this Vmax, and what was my, let us also remind ourselves what was this E. So this E was some number, okay, and 1 by VR for the case of this, right? So if I want to calculate the minimum energy, okay, so it should be this number. The entire thing should come, and then this will be, yes, it will be Vmax, right? You see, for this I don't need to do any calculation. This is given. Once you set up a leisure lab in your lab, wherever, this is given. You have something called a conversion factor. You need not know. There is a power which is whatever you have availability. You put that, and this gamma is in whatever medium you work on. Once this is given, you can use this formula, and then immediately there is a minimum energy, right? So even if you try hard, right, you cannot go below this energy. After that, there is no guarantee that you can successfully do this experiment. Okay? So this is the final plot which I would like to make in the context of experiment. So let's say that I want to make a plot of energy with respect to the velocity. So I have okay, this is something I want to make. So initially I was assuming that, okay, like this can be indefinitely, like I can make it slower, right? I can make it vanish almost, right? But now what we have seen that we cannot actually do that, right? So what will happen? So it actually will go down, right? Because you see that it goes as 1 by VR, so it goes down, but then it saturates, right? And this saturation point essentially is, what is the saturation point? Vmax, right? So it doesn't matter after this velocity, okay, whatever you do, the energy is essentially fixed. This is the maximum you can do within this given setup, okay? And now, of course, now if you think about, like working with some other kind of protocol, etc., instead of having constant velocity, you can again, like think about what is the minimum energy with respect to that protocol, etc. But this particular, like this relations, whatever we have done here, this doesn't change, okay? So if there are any questions, like this is a good time to ask. Yeah, please. Sorry? There is no Vmax, there is no resetting rate in Vmax, right? No, this gamma is the viscosity. So that's what I said. So this Vmax, right? So this Vmax is already decided way before, right? Somebody made an optical trap. It's already decided what you can do with that optical trap, right? So this is what you can do. If you want to move the trap with certain velocity, it has certain constraints. And that depends on the power and the medium on which you are working on, etc., etc. Right? Okay? This is something which you understand, right? Because you have a very, highly viscous medium, there will be a certain different velocity. It will depend on all these parameters. If you give a very high power, then of course the particle can move fast. The trap can move fast, right? So all these things, of course, now you can join the pieces, right? Okay, so I think I have been able to sort of convince you, what goes on when you would like to do an experiment with resetting. And there are also other kind of resetting experiments. I have not found time to discuss about them. But I think within this setup, which is quite some general and has quite some flexibility, we have seen, what you can do. And you can think about energy trade-off relations and many other, other important details. Okay? If you have any questions, this is the right time to ask, and then because I want to switch to something else. Yeah? Okay then. Okay, so this remaining half an hour or so, the plan is basically to, to give you also like some other kind of applications of resetting, okay? And now I would like to, focus on something else completely, okay? Probably which you do not have much knowledge about.
I have one question. So let's say I
yes.
have using ion trap, I trap the particle in center,
Hmm.
and I oscillate the medium.
You oscillate the medium.
Yeah, the medium, and the
Okay.
particle is trapped in center.
Okay.
So by looking at how the particle moves, it can also give the viscosity of the.
I think yes,
Yeah.
right? Yeah.
So I wanted to like, what is then physical significance of resetting here?
See, the physical significance of resetting also in this case is nothing inherent to the system, right? So viscosity, what you are talking about, right? That is the property of the medium itself, right? So this medium is set up, right? You can play around with this optical trap in whatever way you want. We wanted to understand that if I want to do a resetting experiment, how should I actually construct it? So I say that, okay, a simple setup is you put an optical trap, right? And then let the particle first diffuse. At some random interval, what you can do is you can project the trap on this particle. And then you can bring it back, right? In all this mechanism, you actually do not change the viscosity of the medium, etc. These are all all the parameters essentially are kept fixed. Only the manipulations, such as, for example, the velocity, etc. This is something which you externally control, right? You have complete control over all these things, and that is what we are using. We look into different velocities, right? We also look into different resetting rates, because these are the quantities over which we have completely control of. Correct? Yeah.
You don't use this method to find the transport property of medium.
No,
Okay.
not at all.
Then
What we look into these spatial properties of the particle under resetting mechanism.
Okay.
And basically, more importantly, the focus was, we went to this regime of instantaneous resetting to non-instantaneous resetting, right? We wanted to understand the effect of different type of return protocols. This is all I have done in the last 1 hour or so.
Okay.
Yeah?
Yeah.
Okay. Okay. So what I would like to, discuss about in this final half an hour or so is possibly one or two applications. And the first application which we are going to study is something called queues. Okay. Okay. So what is a queue? Where do you see a queue? Come on, in the supermarket, you came by flights, right? You have this long queue, right? And you have this, you want to, change your something, I don't know, Amazon, order or something. You are in line, you are waiting on a queue, right? In the call center. So there are these queues are ubiquitous in our life, right? You cannot escape them, okay? So queues essentially is also a very advanced field of research, okay? Usually not well studied in physics, so to say. So this is a field which is known as operation research. Okay. And there is almost persistent effort, okay, for the performance modeling of different type of queues. Okay. What do I mean? So for example, right, you have gone to supermarkets, right? And now I think there are many tailors, right? Tailors essentially means the service person, okay? And then I think in the last 5 years or 6 years, right, we have seen that there is something called an express lane, right? You see this, right? Why do you think this concept came? Okay? So these are essentially performance modeling, right? Because there is a active field of research who deal essentially with these practical problems. Okay, these are really practical problems, right? And some people have to handle these problems, right? They have to come with different type of strategies so that they can mitigate these issues, right? And this is the field which we call operation research, okay? And queues, of course, in mitigating long waiting times or long lines, etc. This is, of course, these are of grave importance, okay? So what I would like to motivate you or try to convince you at the end of this particular discussion that if you do reset, apparently, I will also explain what we do, what we mean by reset. You can actually significantly reduce, this waiting time you have in a queue. Okay? That is what we will do. We'll do systematically. Okay? Okay, so first of all, forget about resetting for the time being. Let us first define a queue. Okay? How do we define a queue, right? So it's a very simple, okay? So queue is a very simple stochastic process, okay? Just think about it in the following sense, okay? Okay, so this is my service station, okay? So this is my service station. There is a person sitting here, okay, who is serving you, okay? Whatever it is. Is there a supermarket or a call center, visa immigration, in the airport, somebody is giving you the boarding pass, right? And then there is a job, okay, which is constantly coming, right? And let's say this is coming with a rate lambda, okay? This is basically one job, this is second job, this is third job, right? Okay? And we are in a civil society, so we are not crossing each other, okay? So essentially, an assumption is first come, first serve, okay? Okay, so this is my queue. So I have some guys here. This is something which we call jobs, okay? Okay, there is a service station, okay? And these jobs are arriving in this queue with certain rate lambda, okay? So this is the definition of queue. That's it, okay? Now, what are the quantities we are interested in? We are interested in the quantities, in the following quantities. Given I arrive here somewhere, okay, what is the typical time I have to wait? Okay, how many guys are standing in front of me, right? Obviously, these are the natural questions. The first thing you do is you just look for, like which queue is the shorter, right? I would like to go there, right? That is what you're doing. Keeping in mind that, okay, this has less number of people, like if I go there, the service will be faster, right? But how many times do you think this is actually correct? Yeah? So, like there are different parameters. And this is one by one, we are going to come to address all these issues, okay? Okay, so, the stochastic variable in this problem is the number of jobs, essentially, which is being served. So, in 0, 1, 2, infinity, right? Because there is no upper bound on the number of jobs. It just keeps on coming. Okay. And like these are like more like terms. You need not know this, but I will introduce to these terms. Okay. So this is called an NG1Q. Okay. Via Kendall's notation. So Kendall essentially gives this, made this nomenclature, so that's why we call it Kendall's notation. What is it? It's very simple actually. This stands for Markovian, okay? What is Markovian here? The arrival process, because the arrival is happening with the rate lambda, okay? So if it is happening with the rate lambda, so it's a Markovian process, right? Okay, so this is Markovian. What is this G? G stands for general service time, okay? So, general service time. What does it mean? So, I have this server, right? There's a service person. This person is, she or he is serving us, right? And that has some fluctuation, right? And that service time has this distribution, which is not necessarily Markovian. Okay, in the sense it's not necessarily exponential. Okay, it could come from some random distribution. This is the reason I am giving it a general arbitrary FST. Sorry, jobs, arrival of the jobs are Markovian. Okay. And this one is rather simple. This is actually this guy. Okay, one job at a time. Okay. There are no 2 or 3 guys together like, we are friends, etc. Please, no such business, okay? No. This is no. This is what you mean overwrite each other?
So this is the ideal system, right? Because one cannot just go
This is, I would say, this is a civilized thing. You know, like not an ideal thing. This is a civilized. This is the way we should all operate. You know. But of course, yeah, this is an idealistic system. Yes. Okay. Let's see what else. Yeah. So one job at a time, right? Right. Okay, because I have defined a distribution, right, it will have certain mean, right? So let's call this as, denote this guy as S inside angular brackets. And these, something called mu inverse, okay? It will be clear in a minute what I mean. And there is a very important quantity which usually is defined in queuing theory, okay, especially in MG1Q. What are the parameters I introduced here? There was lambda, and there is just mu, right? This is basically this, right? So you can actually come up with a number. It's called utilization parameter, okay? I will explain what is it. So it's given by the ratio by lambda by mu, okay? So if you see, this mu is essentially S average inverse, right? And what is this lambda? Mean arrival times, right? Right. So this is essentially, this is the ratio, okay? Right, because the arrival is taking place at lambda, rate lambda. So what is the mean arrival time? 1 by lambda. So that is what I have written. 1 by lambda, S is 1 by mu. Fine? Okay. Now let us discuss the following thing, right? So let's say that what happens when your, you know, like lambda is very higher, very much higher than mu, then what can happen? Just think about it, you know, not mathematically, just look into this one. There is a person who has a certain amount of, you know, like mean service time, right, on an average, right? And now there is a lambda, which is the arrival rate. Now if I have an arrival rate, which is higher than the rate at which I am being served, then what happens? Yes, exactly. So it will just pile up, the jobs will just pile up, right? So this is something, so rho reaching 1, okay? This is basically piling up of jobs, okay? So just to keep things physical, what we will assume? We will assume that this rho is always less than 1, okay? So that the system is in steady state, okay? What do you mean system is steady state? Is that on an average there is some certain number of jobs in the system. There is no piling up, okay? So something like this is an assumption we will make, okay? Very simple assumption, okay? Okay. Now let us come to this fundamental question we asked, right? So typically, let's say that I have this queue now. I'm usually very bad at drawing, so let me just. I don't know what is it. So, okay, so this is some arrival, okay? So let's say that I arrive at some point of time, and then I have to wait, right? So I have to wait, and I'm interested in this waiting time, etc., right? Okay, and then the number of jobs which are, you know, like waiting before me, right? So let's say that interested in the number of jobs. Okay, or the you know, like the waiting time. Okay, this is the question, right? Okay, and what do you think this should depend on, right? Anyway, I've made the drawing there, so I can erase this part. Okay, so the jobs are arriving at a rate lambda, right? And I also arrived at a rate lambda at some point of time. And typically there are, you know, like jobs before me, right? And then of course, you know, I arrive at different days. Okay, this, you know, arrival processes are becoming, you know, like like our favorite thing, right? Again and again on the over the last 4 days or so. So and typically I will wait for some time, right? And what is this waiting time? This waiting time or this average number of jobs, okay? Waiting time and average, basically they are related to each other by just lambda, so it doesn't matter. One of them, let's say this one, okay? What this mean number should depend on? It should be a function of what? Think about it from just, from your experience. Don't think about it from the mathematical point of view, okay? So this number of jobs before you should depend on what? What are the parameters you have, right? Service, right? And this arrival, correct? Service, then you will typically think that the rate at which you are being served, right? So it should be a function of S average and then arrival, right? This is what you will typically think, right? Now here comes the, the non-intuitive part, okay? So people have calculated this number, okay, this average number. And what they have found is the following. So this is actually not only true, okay? It also depends. It also depends on the fluctuation, okay? This is non-intuitive, right? So you were thinking that, it will just depend on the rate at which I will be served, right? But it so happens that actually it is not true. It also depends on the fluctuation this person has, right? So not only at the rate, but also on the fluctuation. Now this is something, we have encountered again and again and again, right? We see that there can be two distribution with the same mean, but could have very different fluctuation, right? So now you can already see that there is something, non-trivial over here. You wanted to ask something? Okay. So this formula was derived by Polachek and Kinchin. So we cannot, we will not be having time to derive this, but let me just write this formula and let us discuss what is it. So this n average actually depends on the following quantity. So rho 1 minus rho, okay? So remember rho, right? Rho is this utilization, which is below 1. And then we have rho square 2 1 minus rho. Just accept this as a fact, okay? And then we have, again, this notorious quantity, right? By this time, I think we are all familiar with this guy, right? The CV, okay? Okay, so what is CV here, right? So this is the mean number of jobs, right? I have, and what is this CV? So let's see. So CV is this, right? So it's just the ratio between the standard deviation and the mean of the service time. Now what do we see, right? So if we see that when you have CV very high, so if you have a high variability, so number of jobs essentially piling up, right? So essentially it means that it doesn't only depend on the arrival rate, okay, or the service time. It is also highly sensitive to fluctuation. Okay, and what kind of fluctuation? Service time fluctuation, right? CVS, right? So this is the quantity which is for the service time, the person who is serving, right? This is the picture you have, right? This is the server. This guy is coming from the distribution. It has a mean and the fluctuation, right? This is what is coming here, right? CVS is sigma by this, right? So this is sensitive also to service time fluctuation. Okay, yeah.
Is it very obvious that we should not care about the full form of the distribution and only should care about the first order?
So this is the first order, meaning like second order, you mean, right?
I mean, is this like an approximation or is it an exact?
Yeah, of course, there are certain amount of approximations here, but this approximation you can safely ignore. Whatever I say, you know, like the setup I have given, within this it works very well. Okay. Okay, so we have this, right? Now, of course, you know, like we understand that this is basically the number of queues, which initially we were thinking that, you know, like it should be very trivial, it should depend only on S and lambda. We now are having a situation where it depends on the fluctuation. So more fluctuations you have, this will increase. So jobs will pile up, right? So now let us think about what kind of service time fluctuation one can have, right? Now again, go back to the counter, think about it, right? So this is my server, right? Okay, so imagine yourself as a server, right? How can there be fluctuations? Okay, there can be two origins of this kind of fluctuations. Okay, so one is extrinsic. Okay. Okay. So what is this extrinsic fluctuation? Essentially, it means that this is something you do not really have control over, which essentially means that it so happens that you are serving particular queue, okay, where everybody is coming with huge number of things, okay, possible, right? So number of jobs essentially in each queue is very high. It's always coming to you, okay? So this is something which we'll call extrinsic fluctuation. And this is something you have no control over, okay? And then there can be intrinsic fluctuation, okay? So intrinsic fluctuation essentially is that you are somewhat sensitive while serving, okay? You as a person, okay? So in the sense like sometimes you serve faster, sometimes you serve slower, okay? Not only that, imagine, you know, going beyond a person, imagine being a service station. This service station you know, like today there is one person, tomorrow there is another person, and then at the other days there will be some different person, right? So each person will have different ways to serve, right? It will depend on so many parameters, right? Even this one person who is serving today may serve in a different way the other days, right? It will depend on so many parameters, right? All these parameters is something we call intrinsic fluctuation, because this only depends on the service property, okay? Not on the way, you know, the jobs are being arrived, number of jobs, etc., etc. So this variability is not something which we will discuss. We'll discuss only about this intrinsic property. Okay? Okay? Yeah. Yeah. So distribution for the time being, what we are saying that on an average, just assume that this is the same distribution. Okay? But we can try to make use of this property now. Okay? Let's see what we can do. So now we understand, right? What is the source of intrinsic fluctuation? What is the source of you know, like extrinsic fluctuations, right? And now we are interested in intrinsic fluctuation, okay? Which essentially means that, okay, you know, like I am in the service station, right? I am in here. Typically, it takes some time for me to serve, right? Okay. And that gives rise to all this fluctuation, etc., etc. Now let us restart this process. What do I mean restarting this process? Just the service, okay? Just the service, and also with this condition that it's intrinsic. So it essentially means that, you know, like there is a person who was serving, okay? Somehow, you know, like the higher management saw that this person is slowing at a very small rate, okay? So, you know, like remove this person, bring another person, okay? Okay, so as if like you are just restarting this process, right? So what is happening, right? So instead of having this random variable, which was exactly active at this point, when you bring a new person, this person serves with a different random variable. Okay? So this is what we call service resetting. Okay, so you reset the service. So instead of having like one person being served, maybe, you know, like let him take some break, bring in another person. Of course, the distribution doesn't change. This is a big assumption. Yeah, the distribution, you're not changing the distribution, okay? Assuming that, you know, like it had all the moments typically same, okay? But it's just what you are doing is just not allowing this person to serve for a very long time. Okay? So again, I can have this schematic. So I have this. So typically, like this is the time it will take, right, to serve. Now what you are doing, you're saying that, okay, in between, you just restart the process, okay? So in effective words, it's like you remove this person, bring another person, okay? Or draw a new random variable, okay? So this is the way we would like to think about it. So this is like restart, okay? So now this entire process will be now replaced by this SR, right? So this service time under resetting, right? So again, I can write the same type of equation which we wrote yesterday, right? So SR is S if it is successfully completing the service, okay? If not, then let it work for some time, okay? This is that some time R, and now reset the process, bring in somebody else, and let this new person serve, okay? So that will be coming from the same, but a IID copy of that, right? Okay? Yeah.
Assuming that the difference between service times after each iteration are small?
No. There is no, there is no particular assumption to this, right? Whether we will gain some benefit or not, that's a different question. There we will have all these things, conditions coming. Okay? Right now there is nothing. I have not assumed anything, right? I am just writing, again, some sort of a renewal equation, right? Just for the service restart. Okay? And then, of course, like once you have this, you can use this formula, which we had, right, the other day. So minimum of R right? Okay, and similarly, you can also calculate the fluctuation. Okay, so this is something which I have not shown the other day. Okay, and it's a bit more convoluted, and it will take a bit more time. But just assume that you can, like derive this guy. Okay. Now, in particular, like let us go back to our favorite restart time, right? So our favorite restart time is exponential. So if you do that, so like you have all the formulas, right? I'm not rewriting them. You know how to write all these things, right? Now there is something which like I didn't mention the other day. Okay, so you can calculate SR, right? Right, and then for the diffusion, you remember that I optimized this guy, right? You remember this optimal resetting rate? We spent some time on the optimal resetting rate, right? The continuous transition, discontinuous transition for general process, how that depends on CV criteria, etc., right? We spent some time. Okay, but there is something which we did not discuss, that using this property, okay, there is a very general relation you can derive for any arbitrary stochastic process, okay? And that relation is something like this. So you can show, okay, so both this process, okay, when it is exactly at optimality, this is always 1, okay? So if you have a mean time, okay, imagine the original problem, like you had this original problem, right? We have calculated this T, right? This T and S here is the same, right? It's just the service time there. We had mean first passage time under resetting, right? Here you have service time under resetting. So if you just optimize this guy, right, at R star, okay, and you can use that relation and put it back in the fluctuation, and you get a relation which is something like this, okay. You see that it doesn't really depend on what is the form of S, okay, but it only holds for Poissonian resetting. This is what I have used, like I have used the small r, okay. So this is an additional property which I have not derived, but just assume that this is true, okay. This is a universal relation, okay. Now what do? We have this guy, right? Let us now come back to our Polacek engine formula. in the presence of resetting, right? So tell me how it should look like, right? So everything will be just replaced by a R, right? So NR is equal to rho R. Tell me. Rho R divided by 1 minus rho R. What is the next term? So rho R square, right? 1 minus rho R. There was a 2. And then we have. Fine? So this is the mean number of job under resetting. Okay? So I have just replaced that original Polacek engine formula, just replaced everything by R. Okay? In practice, what I have done is that rho R is initially, what was it? Rho was lambda times S, right? Right? So what we have done, we have now taken rho R is equal to lambda times SR, because the resetting has been introduced only to the service, right? So I've just replaced this S by SR. And all these quantities, only the fluctuations, like for example, S square or the CV square, right? These are now all SR square or CV SR square, right? That's all. I'm just replacing everything, the same formula, just wherever I have the service, I'm just replacing them with service under resetting, right? Where I know what is this formula, this SR, how it is related to this underlying process, right? I know all these things, okay? Well, it looks like a typical, like some sort of a mathematics, etc., right? Now let us look into the following case. Now you have this SR, right? Mean averaged, mean service time, right? So let's look into this. So you have this mean service time, and you have complete freedom of choosing restart rate, right? So if I plot this, okay, so then there will be an R star, right? There is an optimal resetting rate. And now what we have, I just told you that CV at this optimal, this is 1, right? So now you see that if I put it here, so it's the same as CV R star, this is the way I'm defining it, okay? So you see that if I, I look into this Polacek engine formula for an optimally restarted service process, then this guy is 1. So this entire term disappears, right? So this is 0, okay? So this is 0, and what you are left with is this. So you have N R star, okay? So this is rho R star, right? Okay? This is what you are left with, okay? So well, now, you are saying that you would say that, okay, you got a new formula, etc., etc. It seems that you got rid of this fluctuation term, okay? So what did we gain actually, okay? So now you can do like this one step, okay? So you see that we have this, right? So let's look into this. So we have SR star, right? So service time under optimal resetting, right? This is lower than this one, right? Correct? Because I am at the optimality. Look into this plot, right? I am here. So it has to be lower than this, right? Lower than the original process, right? The original process is somewhere here. Consider that to be finite, okay? It's not going to infinite. So this is true, right? So I multiply both sides by lambda, okay? So what is it? This is what? Rho R star. So this rho R star is less than rho, right? Now you apply this over there. So then we will be able to show that NR star actually is less than N. Okay? So what we have been able to show, right, if you do the service resetting, you see a dramatic reduction in the length of the queue, okay? And similarly the waiting time. It's just because, again, it it is again going back to the same thing because we started with a process which is very much sensitive to the fluctuations, right? And when we restarted this process, we essentially eliminated these fluctuations, okay? Especially at the optimality, you can use this particular universal relation, and you can explicitly show how this mean number of jobs got significantly reduced by the introduction of resetting. Okay, so this is how you can use this classic queuing theory, results from the classic queuing theory, and try to introduce the concept of resetting and show that how you can mitigate this very long number of long waiting times or very long queue, etc., by introducing resetting. Okay, and when I introduce reset, you just keep in mind that there is a service person. This person was serving for some time. Let this person take rest. Bring a new person. Okay, and this is the way it works. Okay, and finally, I just want to make a comment, and then I will stop. So if I want to now make a plot, I want to make a complete plot, so that you have a take-home message. So you see that I'm plotting here the mean number of jobs as a function of resetting rate, okay, as a function of CV square of the underlying process. Okay. Okay. So now let us look into the possibilities, right? So we had this CV is equal to 1, right? And we have a possibility that when CV is greater than 1, then we know the resetting always helps, right? For CV less than 1, resetting doesn't help, right? So if resetting doesn't help, so I have an R star which is 0, right? So then the original formula doesn't change. So the original Polaczak-Kinchin formula, it essentially remains the same. So you have something, and then it was proportional to CV square, right? So if I make a plot, so the original formula basically will look like this. It's linear, right? CV square, okay? But now look into this restarted process. Exactly at CV is equal to 1, right? I'm somewhere here. If I now calculate this NR star, right? As a function of CV, I know that it is actually will start decreasing. Okay. So this is the original process, right? Which was just a function of CV square. You look into your note, right? It will just go linearly. But then as soon as you introduce this resetting process, right? Then we know that for not all the CV resetting works. When CV was less than 1, it just goes along with the old line. Nothing changes, right? But as soon as you cross this CV is equal to 1 for the underlying process, then you know that resetting is going to help you, right? You already know by that time because you have a finite R star, you can go to the optimality, etc., use these relations, whatever you have done, and suddenly you start seeing the reduction of this. Okay? So you see that you started with, with a queue which has large fluctuations, etc., and by introducing the service resetting, you can see a drastic reduction for the number of jobs in the queue. Okay? And of course, there are many more things you can do. We have assumed the exponential resetting rate or our favorite Poissonian resetting. You can actually imagine that doing resetting after a fixed time, okay, instead of having this, what we assumed here was this, right? This. So this was still a rate process, a random process, right? Instead of doing that, you could have a stroboscopic process. This is something which we call sharp resetting. So let's say that only after every t time, you will just do the resetting, okay? Then if you just continue doing this thing, of course I didn't derive any, any formulas, etc., for such kind of resetting distribution. But you can go home and do these calculations because I have shown you the general formalism. You can use those formalism. But I will just show you here. It will so happen that for the Poissonian resetting, you had a reduction, right? Now, if you apply sharp resetting, you will start seeing that, this reduction will start even before, okay? So it will start even below CV1, okay? And it will reach even faster, okay? So essentially it means that, like instead of resetting at a rate r, if you could have done resetting after every fixed number of fixed time steps or something like that, okay, which I'm assuming to be t, then you can even, like reduce the line even further, okay? Okay, so I think I will stop here. I think I have been able to, at least introduce you, to this concept of resetting and some general formalism, how you can apply them in practice for some very broad class of search processes. Then I have been able to show you at least how you can solve it, how you can actually visualize a resetting experiment. And then, of course, I didn't get time to get into this enzymatic reactions, etc. But at least I'm happy that I was able to show you how you can apply this resetting in an example of operation research, namely the queuing theory. So I hope that you have taken something from this course. So thank you very much.
So we'll still have a tutorial, but this was his last lecture, and let's first thank Arnav for a fantastic set of lectures. Okay, so this also brings to the school to the formal end. So we'll still have the tutorial. Okay, but okay, so let me just end the school by, first thanking all the lecturers, because, they have put a lot of hard work, and I think they did a fantastic job. And let's thank all the speakers. So after that, of course, big thanks goes to all of you, the participants, especially all of you who stick till the end, and it looks like you still want to know, and probably you can go for another 2 weeks of school. But okay, so actually, I think all of you, have been very fantastic and very interactive, and that matters a lot for the success of a school. So big thanks to all of you. Okay. So they will send you a feedback form, and you don't have to sign your name. So you just give whatever honest feedback, good, bad, ugly, whatever this thing, right? So that helps us to organize the school next year. So the feedback from the participants is very important. So thirdly, of course, money is very important to organize any such activities, and it costs a lot of money. And so as you know, that this school was jointly organized by ICTS and RRI, and let's thank both ICTS and RRI for funding the school, right? And as you know, that money is not enough. I have met my colleagues from various other institutes, and they always said, okay, we got this money to organize this conference, but our staff is terrible, and we are scared to organize this. So fortunately, actually both at ICTS and RRI, we have fantastic staff, and that includes secretaries. There are a lot of things goes on in the background. You have probably only seen people who have written to you, the secretaries, Gayatri or Kaivashri from this thing, but there are a lot of other people, for example, IT staff who have been sitting there. There are also IT staff at ICTS who are doing background thing. There are people who are there all the time serving coffee, etc. So I think a big thanks to all the support staff from ICTS and RRI. Yeah. And I think this brings to the end, and I hope that you have actually gained something. And all the lectures will be online. It is still online in the YouTube, but it will be put on the talk pages both at ICTS and RRI. Probably now it's not completely synchronized, but it will be synchronized in a week or so. And hopefully I'll see you, a large fraction of you, next year, I guess, right? Okay.
Guys, I want to take a selfie with all of you guys. Is that okay? Is that okay? This is within the discretion? Okay?